Good morning. Please take a seat. It's 9 o'clock, in case you haven't noticed. And welcome to the first session for today, Tuesday. We are starting with Science Session 1 on microwave CNCI surface temperatures, algorithm development and operational and research applications. Danielle is the co-chair, and my name is Joanna. I'm chairing this session. Nice to see you all here fresh. And we will be starting with Wenyu Wang on sea surface temperature retrieval from Himawari 4A microwave imager, combined active and passive. Thank you.
Okay, good morning, everyone. I'm Wenyu Wang from National Space Science Center, Chinese Academy of Sciences. Today, I will present our recent work on the MICAP, the microwave image combined active and passive on board Chinese ocean salinity satellite HY4A. Okay, let's start with a brief introduction of the mission. The HY4A is a part of Chinese Ocean Satellite Mission, and it was launched on November 14th, 2024. And there are two payloads. The first one is LASTMR. It is a two-dimension L-band synthetic aperture radiometer developed by CAST. And the second one is MICAP, microwave image combined active and passive, developed by our library. MICAP has three one-dimension synthetic aperture microwave radiometers at L-band, C-band, and K-band, and it also carries a digital beamformation microwave spectrometer at L-band. The satellite feature is the altitude maneuver for cold space calibration and uses the high stability thermal control to improve the system's sensitivity. Okay, MICAP has synthetic aperture resolution at in the cross-track direction and has real aperture at along track direction. So the footprint of L-band is 50 kilometers by 75 kilometers, and the 15 kilometers by 25 kilometers at the C-band and K-band. For SST retrieval, the C-band is the most relevant, so the synthetic aperture can provide a relatively high spatial resolution at C-band. And the noise performance is also promising. The NEDT at L-band is better than 0.15K and better than 0.5K at C-band and K-band. Its source width in the alliance-free FOV is about 1,200 kilometers. The level 1B data provide TB at snapshot pixel. MICAP get the line measurement in the cross-track direction with the incidence angle varying from 32 degree to 55 degree in the alliance-free FOV. And the level 1C data provide the TB at Earth grade after ocean target transformation. The OTT is calculated by the difference between the observed and the simulated TB over a fixed cycle for L band and calculate once as a fixed value for C band and K band. And the data projected onto two equal area grids at 15 kilometers resolution. So before retrieval, we perform an analysis of the observation minus background. The simulation data using the ISS-RTM. So there are two major problems we can see in the OMB map. The first one is the IFI, especially in the C band. We can see from the from this area, it appears as trip-like features in the OMB map. And the second one is strong land sea contamination. We can see near the land, it is strongly contaminated. As we evaluated the distance of the snapshot center to the coastline, if this distance larger than less than about 1,300 kilometers, the land will get into the FOV of the instrument and will contaminate the whole snapshot. So quality control and outline filtering is still needed in current version. Okay, the level 2 operational processing, there are two modes currently in our processing flow. The first one is the L-only mode. It only uses the L-band TB to retrieve salinity, which is like the smooth. And the second one is the cap mode. Cap mode will first use the C band and the K band to retrieve the SST wind speed, water vapor, and liquid water, and then use the L band radiometer and the spectrometer to retrieve the salinity and the wind speed, which is like the cap method of Aquarius. The focus of this presentation is the SST product. Currently, it is not in official operational processing flow. It's only be a subsidiary product in the L-band salinity retrieval. But we have developed the SST product in NSSC, and it will be retrieved in the C-band EASE grid. And we use the optimal estimation method using the diagonal convenience setting, and the LM iterative method is used to solve the retrieval. The input TBS are at the top of atmosphere and in the antenna polarization framework. Before retrieval, 3 sigma threshold, RFI flag, and other way to eliminate the outline is applied, and we use the 3K and 3 meters per second as a priori uncertainty in the OEM retrieval. Okay, let's see the validation results. After the quality control, compare the SST with iQueen Institute data. The whole RMSE is about 0.77K, and of the wind speed is about 1.2 meters per second. However, they are thanks to the outline fielding, there are less data in near the coastline is a problem. This shows more detail about the error distribution as a function of latitude, and the bias is small, but the IMSE increased with the latitude, especially in the northern hemisphere, and the overall trend is consistent with that of MSR2, but MSR2 has much higher accuracy. This shows the different time scale of the MICAP SST, of the daily, 3 days, weekly, and monthly. So the data gap mainly in the near the coastline and in the high latitude, we are still need to improve our data. We tried to calculate the Nino 3.4 index, and it shows a similar trend of with other product. For the future work, there is an internal ongoing work of the deep learning based TB reconstruction. Currently, the result shows that this work can improve the TB at near the coastline in the at L band, and we expected this method will provide a useful way to other band. Okay, for MICAP SST product, we noted some problems, such as strong latency contamination, strong RFI, and some data gap in the high latitudes. So we are trying to improve our data, and we are also collaborating with ICM to improve our data. We hope we can provide more useful data product, and currently that data was the operational data was provided by National Satellite Ocean Application Service, but currently only for Chinese citizens. So scientific data set will be published by NSSC, include L2, even the L1C. I hope we can publish it in at this year, at the end of this year, or early next year. I don't know. We hope to contribute to GHRSST. Thank you.
Thank you very much. Apologies on my behalf for the error on the name of the satellite. It's Haiyang, Kimawari. And next, we have Fumiaki Kobashi on the development of the climate data record of sea surface temperature from the AMSAR series observations. I will be making a note when you have 2 minutes left for the presentation.
Good morning, everyone. I'm Fumiaki Kobashi from TAMSAT, Tokyo University of Marine Science and Technology. And the title of the talk is a development of the climate data record of SST from AMSAR series observation. And this is ongoing research I'm working on in cross collaboration with Kurihara-san from Tamsat and Yoshida-san and Kashi-san from JAXA. So I'd like to introduce our research project and present progress with some preliminary results. Passive microwave measurements are affected by clouds, so they are very important for global SST observations. And the AMSA series has operated successfully since 2002 and providing the foundation of the long-term SST climate data record. And at present, JAXA produces the AMSA SST product using the statistical regression algorithm developed by Shibata-san in 2006, which is well-tuned and validated with in-situ observations. And there are alternative approaches for the SST retrieval. For example, the physical-based regression methods developed by Wenz and Meissner 2000, and the more optimal estimation method more recently developed by Nielsen English et al. 2018. And though the JAXA's products are well-tuned with in-situ observations, some issues have been identified. Left panel is a 6 GHz SST around Japan, and the right panel is a SST gradient, which highlights the small-scale features. So you see the strong SST front along the cross extension, and also you see some stripe noises. And this noise may come from the 6 GHz brightness temperature. And another issue is spatial resolution. The spatial resolution of the 6 GHz is about 50 kilometers based on the footprint. However, the comparison with the infrared SST estimates the actual effective spatial resolution about 67 kilometers, so indicating the significant degradation. And this is possibly due to the over-smoothing in the JAXA's product. So the objective of the study is to construct a high-quality long-term SST climate data record from the AMSA series observations. So we aim to retrieve SST as independently as possible. So the conventional method usually rely on the a priori SST information from other external data set for initialization and references. So as a result, they are not fully independent. So in this study, we minimize the use of the external data set to retrieve the SST. So independent data should be useful for not only the research, but also for model validation. And currently, we are developing the algorithm for the AMSA2 observations. So these are characteristics of our climate data record. We will produce the L2 and L3 products of subskin SST and the sea surface wind speed, mainly using the JAXA L1B data. And we apply the optimal noise filter to L1B data to reduce the stripe noise. And then we also conduct the cross calibration using infrared or SST data. And these two processes, noise filtering and the cross calibration, significantly improve the quality of our climate data record. And we also developed the coefficient-based physical retrieval algorithm to produce independent SST data. And we evaluated the spatial resolution, focusing on the effective spatial resolution, which, as I mentioned, may differ from the nominal resolution. And we will not interpolate no observation area using either AI-based and statistics-based interpolation techniques. So these are main algorithm components. The first one is optimal noise filtering, and it works pretty good. And the filter removes the stripe noises effectively without degradation of the spatial resolution. And Kurihara-san presented the poster, the result in a poster, so please visit his poster. And the second one is a cross calibration. We have developed the original method, which uses the physical MSS data simulated using the Beers SST. And yeah, the development is almost completed, and the Kurihara-san will present at this coming IGRS in August. And the retrieval algorithm is still under development, but it is basically the physical retrieval to create the lookup table for SST and the sea surface wind. And the final components validation, including the spatial resolution assessment and accuracy assessment. So we will feed the validation result back into the three development processes to iteratively improve the accuracy and the algorithm. Okay, so this is the algorithm flow. We use the AMSR2 L1B data, and we perform the noise screening followed by the cross calibration using the Beers infrared SST and the sea surface wind. Using the calibrated data, we retrieve the SST and the sea surface wind using the lookup table developed by the physical retrieval algorithm. And this is a validation. We carry out the spatial resolution assessment and accuracy assessment using the infrared SST from geostationary satellite and the polar orbiting satellite, as well as in situ observations. Okay, so this is the output from our processing. The subskin SST and the sea surface wind speed at 2 meter height above the sea surface. In addition, we will obtain the supplementary parameters. The first one is the cloud rain fraction. The cloud here refers to something that affects microwave radiative transfer. And we calculated this fraction by comparing the observed brightness temperature with the brightness temperature estimated under the clear sky condition. And also we have a random contamination fraction in a footprint. And our climate data record will be compliant with the latest GDS format. And however, it doesn't include these three parameters. So we will add these parameters. Okay, skip this one. Okay. And this is a preliminary result. It's a SST in Kelvin. Currently, we don't mask the sea ice areas. So except the sea ice areas, the overall distribution of SST and the SST value itself looks good and reasonable. And this is sea surface wind speed. Again, it looks reasonable. Yeah, capturing the strong winds in the equatorial region and some of the extratropical low pressure systems. And this is a snapshot east of the Japan, typhoon east of Japan. And the right panel is a 6 gigahertz buoy brightness temperature, and the middle panel is estimated SST, and the right panel is the sea surface wind speed. So yeah, we needed to check the accuracy, but the result successfully captured the lower SST under the typhoon and the strong winds of the typhoons.
2 minutes.
Okay, thank you. This is a preliminary accuracy of GHRSST, and it is calculated by comparing the in situ V data, and the robust standard deviation is about 0.789 degrees Celsius. While the uncertainty come from the sensor noise and the algorithm, a total 0.68 degrees Celsius. So I think our results look promising so far. And yeah, we can further improve the algorithm for better accuracy. Okay, so this is it's a summary. We constructed a high-quality long-term SST climate data record from observations, and we have developed the algorithm for the MC2 observations, including noise filtering, cross-calibration, SST retrieval, and validation. And we have good, promising results so far. So we will continue the further improvement and the developments. Thank you.
Thank you very much. And next we have Misako Kachi on the overview and current status of the Advanced Microwave Scanning Radiometer 3 on board the GOSAT GW satellite. Thank you.
Okay, thank you, Chair. So it's my pleasure to present the status of the AMS-3 in this opportunity. I recall the last year's GRIS meeting. So that was the just before the launch, and I quickly back to Japan for the preparation for the launch. The launch was delayed 1 week, but it's after that it's successfully launched. So I'm happy to show the result. Oh, sorry. So these are my colleagues who contributed to the presentation. So the SST observation from space, and of course the GRIS members are aware of this one. But we have the two kind of the observation sensor type. The one is microwave imager, and the other one is IR imager. And for the IR imager, we have the two kind, and the polar orbiter IR image and in a traditional spatial resolution, and also the geostationary IR image like Himawari or GTS or the MTG or the GOES satellite. So those things, the microwave images advantage is cloud free. And polar orbital IR image it has a quite high spatial resolution. It's quite advantage. And the geostationary IR image is quite the frequent observation is available. So the three has a different advantage and maybe this disadvantage. So for here is the comparison of the IR and the microwave SSTs. So the infrared is for the cloud area, so infrared SST is not observed, but microwave is correctable. Or near cloud area is contaminated in infrared, but microwave is not influenced. And also the rain area. So recently the microwave it started to estimate the rain area. So it could be maybe as maybe we can change to the correctable or something. And also the water for the aerosol, microwave is not influenced. The water vapor is correctable, and also also sensitivity and also the influence of the sea surface wind speed is correctable in the microwave, and sun grain was contaminated, and near round area is also contaminated. We needed to do something, and the spatial resolution is for the microwave is quite low compared to the infrared. But those are the differences quite important for when we use the microwave imager. So I picked up this slide in almost 20 years ago. And in the year of 2002, in a second TRIM conference in Hawaii, I presented the early status of the AMSA-E SST with the TRIM TMI microwave observation. The TRIM TMI has the 10 gigahertz channel, and the rest one is the SST estimation from the microwave radiation in SST and the brightness temperature. So for the 10 gigahertz, 10 gigahertz vaporization has less sensitivity to the lower temperature range, and for the 6 gigahertz, which is can be available in AMSA E and AMSA, so it's a 6 gigahertz has a more sensitivity to the lower temperature zone. But for the TRIM, case of the TRIM, the TRIM is observed only in the 35 degree north and south, so it's usually there's not much that go to the lower temperature area, so it could be it is nice. And then it's that there's a comparison with the TMI and the BEARS. BEARS SST, BEARS is also the on board the TRIM satellite. It's a the IR optical and IR imager. So we have had a coincidence observation of those two, and those experiences quite how they contributed to the AMSR activity later. So the AMSR is now coming. So the advanced microwave scanning radiometer is the name of the AMSR. So the first one is that there are two AMSR in a first generation. The one is the AMSR on board the others two, but unfortunately it's only survived the 10 months because of the failure of the platform. But the AMSA-E provided to the NASA's Aqua satellite was continued operation, science operation 9 and 5 years. So from 2002 to 2011. So those two has the 6 and 10 gigahertz channel to retrieve the SST. So it's quite helpful for to provide the global SST in long time period. And also the AMSA-2 on GHRSST satellite was launched in 2012. It's a small gap between the AMSA-E and AMSA-2, but the AMSA-2 is still in operation now, and we can have the expect the smooth transition from AMSA-2 to new one, AMSA-3, that was launched in June, end of June last year. And the AMSA, so those AMSA instrument is the multi-frequency and the dual polarization from low to high frequency range, and the fine spatial resolution compared to the other microwave imager. Of course, and we cannot achieve the fine spatial resolution like IR. But and also the global observation, the water cycle variation is able to do. And from those 3 generations of the AMSA series, we expanded the operational utilization and also the longer observation for the science. Right, so this is the GHRSST GW satellite specification. So we have the 2 instruments on GHRSST GW. One is the AMSA-3, but the other one is a TANSO-3. It's a kind of the GHG instrument led by the Ministry of Environment of Japan, and also the National Institute of Environmental Studies. So they improve the observation of the GHRSST TANSO-2 mission. And then I remember Eddie already showed the launch of the GHRSST GW yesterday. And this is the satellite specification. So the satellite altitude is 30 kilometers lower than the AMSA-2 because of the TANSO mission wanted to have the very finer spatial resolution. And also but the local sun time at the node is the same as GCOM-W. And the designed mission life is now 7 years, so it's longer than the AMSA-2. And it was launched in the end of June. So this is the mission timeline after the launch. We have the critical operation phase for 3 days, and after that, and during that time, we had the satellite separation, was solar array paddle deployment, so 3 antenna deployment, and initial run up in 4 RPM, 4 times per minute, and above the AMSA-3 antenna, and also the release of the pointing mirror log of the tensor 3. And then we go to the initial functional verification operation phase. So verify the main function. So the phase is finished in October 8 last year. And then we started initial calibration and validation operation for the AMSA 3 and the tensor 3. So now we are almost finished, completed this initial calibration and the validation. We will have the kind of the review meeting next Monday next week, and for the data release. So I think that we expect the data release end of June or very early July. So for that to the public. And then after that, we will go to the nominal mission operation phase. And as we told, in AMSAT2 near real-time data will stop end of the August. Responded to the completion. The start of the near real-time data distribution of the AMSAT3. So we asked the near real-time data user to switch the data. But the delayed mode, and for the SST, it will be the almost 1 day. Maximum is 1 day delay will continue, and for the cross calibration with AMSA3. So this is the kind of the radiometric calibration framework. But I don't think that I don't much time. But we have the kind and doing the both the radiometric calibration and the geometric calibration. During the radiometric calibration, so we have the onboard the CSM and the data acquisition timing and the hot load thermal control updated, and the level 1 parameter is also updated. So those the radiometric calibration is conducted during the initial calibration and validation phase. And of course, there is sometimes has the problem, but I believe that we solved most of them. But still, some of the calibration issues is to be solved in a future version, like using the deep space maneuver that was conducted in December last year. So it is too early to reflect those results to this radiometric calibration. So version 1 doesn't include such kind of much about the deep space maneuver. So this is the radiometric performance after the initial calibration and validation. So NEDT, so this is a specification and the ground test measurement, and then on the on-orbit measurement is showing very good status. It's all achieved the specification and better than the ground test. So I think that we can do that much. We did the most of the things for the radiometric performance. And the other one is the scan bias correction. So for the AMSAT2, we also experienced that this is scan biases as an edge of there is a partial due to the partial blockage of the onboard calibration sources. So there will be in a scan along the scan line, then there has a kind of brightness temperature decreasing. Such kind of data signal is found, and when we are showing and making as a monthly average of the 6.9, you can see the small line of the light blue line, and that this is the edge of the brightness temperature is showing quite low, and it's remained. Those things is also corrected in AMSA2, and we are doing the similar method to that AMSA3, and then the result is right hand side. This one is corrected, and also that this the lower panel showing the corrected the scan biases over the ocean region. So I think that we also corrected the scan biases in AMSA3. And the geometric for the calibration, so of course the geometric geolocation error is evaluated using the coastline matching. This is also done in AMSAT2. And also we compare observe the brightness temperature maps with the land sea fraction patterns. So I think that we adjusted some of the parameters for correction. So we showed the geometric error post calibration. This was well within the 20% of the IFOV for all channel. So we showed it as I think that also the geometric correction is also work well. And cross calibration. So we compare the AMSA 3 with the AMSA 2 and the GMI, because the AMSA 2 has the 6 to 89 GHz, but for the AMSA 3 we introduced the higher frequency channel like 166 and 183. So we added the GMI for comparison, because the GMI has the 10 to 183 GHz. And this is a result, and the upper panel is AMSA 3 minus AMSA 2. Day and night time are double differences in 6 GHz and 10.365 GHz. And the lower panel is AMSA 3 minus GMI for 10 GHz. And you may see the small differences between there is a small differences between the ascending and the descending orbit. And so, and also the consistent with previous report, because the AMSA 3 brightness temperature showing the lower than the AMSA 2 and the other and the closer to the GMI, because the AMSA 2 was reported it has a larger biases compared to the GMI. So I think that we AMSA 3 is more similar to the GMI now. Okay, and the products, geophysical product. We have the many geophysical products in like this, and those result and so those are also they compare with the in situ observation, or they sometimes, if there is no in situ observation is available, compare with the other satellite observation. For the case of the SST, for all the product is achieve the release accuracy, or sometimes achieve the standard accuracy, which is expected to achieve within 3 years after the launch. And I think that we are satisfied for the result. And this is the SST validation result. I think the area already shown in the poster presentation in more detail. But and we AMSA 3 SST is compared with the ICOM 2V within 2 hours and 30 kilometer differences from August to April this year. So for the 6 GHz SST and the 10 GHz SST and the multiband is a mixture of the 6 and 10. So those old product is showing good root mean square error from the in-situ observation. And also we compare with AMSA 3 and AMSA 2 in monthly basis for considering the climate data record. At present, we have in a monthly basis, we have the small differences in especially in higher altitude, higher latitude. But the root mean square error is good within AMSA 3 and AMSA 2. But we have I will explain this one later. But we should be a little bit. We need to refine the algorithm maybe in the future for comparison within the discrepancy between the AMSA 3 and AMSA 2. And the impact of the new 10.25 GHz channel, the AMSA 2 introduced the 10.25 GHz along with the original 10.65 GHz channel, because the 10.65 GHz channel has worse NEDT compare to the 6 GHz, and that because the 10 GHz SST has a more noisy pattern of the sea surface temperature, and the 10.25 is not a protected band for the other the communication radio frequency, but we added this one kind of the complementary channel for the 10.65 GHz channel. And as a result, the right-hand side is AMSA 2 SST and the left-hand side is AMSA 3. This is very difficult to see, but these the European area, so missing in area in showing gray is reduced in AMSA 3. And also we also mitigated the reduced reduce the wind and rain impact in tropical region. So I think that will be the has an impact for the 10.25. And the CIS, for the CIS concentration is also validated with the GHRSST data with within 30 minutes differences. And this is showing that the root mean square error is now showing 2.72%. And for the high resolution CS concentration in 5 kilometer resolution for A horn and B horn, and those are the two is also showing that and require less than the required root mean square error.
2 minutes.
Right. And the CIS concentration. So this is the monthly comparison of the CIS concentration between the AMSAT 2 and AMSAT 3 for Arctic and Antarctic region. So you may see edge of the CIS area is showing the big differences between around 5% differences between those two. And also in Antarctic, because this is the this March 2026, and both is the March then from the Antarctic is it's summertime, and then this one is also that we needed to have the investigate further for the future version. So the one important things, orbit difference between the AMSAT 2 and AMSAT 3, because it's the same local time, but a different satellite altitude, and that means the source weather is narrower and different revisit time. So AMSAT 3 has a 3 days revisit time, but for the AMSAT 2 have 16 days. So that's for the 16 days, the AMSAT 2 is kind of the quite averaged the observation in worldwide. But for the 3 days, we have some other biases, the observation interval, observation frequency in some of the area. So the right-hand side is a daily change of the each of the coincidence ratio between the AMSAT 3 and AMSAT 2 in blue color, and orange is global coverage ratio. So in when there is a quite coincidence between the AMSAT 2 and AMSAT 3, that the observation, the orbit of the AMSAT 3 in pink and the AMSAT 2 in green. So it's almost the same places observed. But of course, the AMSAT 3 observation is slightly narrower, 100 kilometers narrower than the AMSAT 2. So I think that we cannot achieve the 100% overlap, but it's almost 95%. And the timing, its global coverage is 75%. But for the one, the coincidence ratio is 60%, so global coverage in 100%. But this pattern is a kind of the cycle in almost 10 days, 9.58 days, and the repeated almost every 10 days, like the coincidence, the pattern, and not the much coincident pattern. But so that means that we not only for the retrieval error, but also for the sampling error may exist between the AMSAT 2 and AMSAT 3. So for the people who will work on the climate data record, may be needed to consider this kind of changes. And we would like to estimate this kind of sampling error in future version. Okay, as a summary, and as I told, it has advantage, and of course you already know that. And just the latest AMSAT 3 was successfully launched, and then we completed the initial calibration and validation phase, and all version 1 product is achieved accuracy. But it's while some discrepancy between the AMSAT 3 and AMSAT 2 still to be solved in the future version. And also the different, due to the difference orbit, and we have the same sampling error between the AMSAT 2 and AMSAT 3. So AMSAT 3 data will be distributed to the public in the end of June. I expect the earliest date will be the 30 June of 30, but I cannot say this is not decided. But AMSAN 3 SST in GDS 2.0 format will be also available to the JAXA GRIST server immediately after we start the public data distribution. So if you had an account of the GRIST website, so please check and data. And we will make an announcement also to the registered users for the data distribution. Thank you very much.
Thank you to all three speakers. And we now have a 10-minute period for questions to the first three speakers. If anyone has questions, please use a microphone. Chris?
I have a question for Fumiaki-san. I saw the two uncertainty components for the SST and the algorithm component. I wondered if, as well as quantifying its magnitude, we also understand the correlations in space of the errors that happen with this component, and which physical factors determine the correlation in space of the errors in the algorithm component.
Well, yeah.
Thank you for the question. The algorithm components are determined by using the numerical simulation related to transfer. So algorithms, SST and SSW are determined using a lookup table. So the uncertainty is calculated in each lookup table.
Okay, thank you. Can I have a second question to Misako?
Go ahead.
Thank
I'm
you.
not going to stop you.
Misako, I was intrigued by the reduction in the gaps from using 10.25 compared to 10.65, which is not a big change in frequency. What's the physics behind less sensitivity to rain?
For the rain? No, not much other physics, but how say that in answer to 10.65 has a quite noisy, and we cannot distinguish the actual the signal and the noises in only using the 10.65. But when we compare with the 10.25, so this nature is almost same, but it's less noisy. So we can check the actual signal and distinguish between the noise and the signal. That will be the improve the algorithm.
Shakila?
I enjoyed the talks very, very much. My question is for, Fumaki? Climate data records. Wow. There's a lot that goes into that. And given the previous talk that we just heard, I'm just wondering from your perspective, what are some of the key challenges that you are facing with generating this climate data record, given the resolution and all the variability?
Well, our climate data record has a advantage in terms of the high quality and independency. So as part of the quality, we have already developed. Sorry, we have already developed the noise filtering and also the cross calibration. But as for the independency, we still have a lot of things to do. As for example, the ice masking and the RFY. So these are the what we should deal with in future. But maybe it's kind of challenging. But yes. Does this answer the question?
Are there more questions? Okay, last one though.
I also have another question for you. You said that you calibrated against veers and in situ wind. And so this involves, I guess, having an emissivity model somehow to compare brightness temperatures in the microwave to the infrared. You need some sort of emissivity model for the microwave. So can you say a bit more about how this intercalibration is?
Well, yes.
Oh, it's also Yuki, sorry.
Thank you. Microwave data is can be simulated only by using SST and SSW. It's very important. Microwave 6 GHz V and H ball data. How do I say? So SST and SSW are estimated only by using microwave 6 GHz V and H. So its inversion is also possible. So 6 GHz H and V are simulated by using SSW and SST. So no. And the emissivity and other atmospheric effects are all calculated in RTM. We are using RTTO. Yeah. That's okay.
Thank you. And we now proceed to the next presentation, which I believe is online, from Robin Ekelund from EUMETSAT on the SIMR Level 2 products for the global ocean and atmosphere status and the way forward. Is
Hello,
Robin-
thank you for, yes, can you hear me?
Sure, and we can see you. Go ahead.
Perfect. Then I'll start sharing. Can you see my slide?
Not yet, but
How about now?
yes. Go ahead, Robin. I will give you a 2-minute note if that's okay.
Perfect, perfect. Okay, good morning, everyone. So yeah, I'm connecting all the way from Darmstadt, Germany. Sorry that I couldn't attend in person. I would have loved to be there. However, I have enjoyed the very interesting presentations so far. So I wanted to give you an overview of the SIMR Level 2 product that we are developing at EUMETSAT with the status and future outlook. And firstly, I acknowledge my colleagues here from EUMETSAT and from partners that have contributed to this development. So I believe that Craig already have given you an overview of the SIMR, and I think many of you are already familiar with it. To give you a quick recap, the let's say primary objective is to provide high spatial resolution microwave imaging and to provide European, let's say, operational continuity for L-band and AMSR type observations in the polar regions. So it's mainly targeting the Arctic, but for the secondary objectives, we also have observations of the global ocean as an objective. So, and also to mention here that this is a jointly developed mission between ESA and EUMETSAT. So ESA has the leading role developing the mission and responsible for the operations, as well as the level 1 and production and the level 2 for the polar and land. And EUMETSAT, we are then responsible for the level 2 for the global ocean and then the atmosphere. And yeah, once again, I probably don't have to go through a lot about the characteristics and specifications of the missions. I just highlight here that the channels range from 1.4 to 37 gigahertz with the CNX bands or channels at 6 and 10 gigahertz. The main one sensitive to the sea surface temperature. And also interesting to mention here is that we will have this circular or this full circular scan viewing geometry. So for each Earth target, we will have both a forward and a off view. And oh yeah, and also of interest to mention is that for all channels or bands except the L band, we will have multiple feed horns, which you can see in this zoomed in picture of the footprint configuration. So for the C and X in the light blue or teal, we see that we have 4 feed horns. And this is essentially to provide full coverage along the satellite track, since the scanning rotation speed is quite slow for Simmer. And about then the level 2 product that we are developing. So once again, as a recap, ESA is doing the level 1 and the level 2 for the polar and land. I believe you will get a bit more information on the polar product in the next presentation. For EUMETSAT, the level 2 product considers, apart from the SST, which is a subskin surface temperature, also the sea surface salinity, ocean wind vector, precipitation rate, liquid water path, and total column water vapor. For the SST, we have the requirement of 0.2 Kelvin in total standard uncertainty on a daily scale, with a 15 kilometer spatial resolution, which is a quite challenging requirement. Some other information is that we are aiming, at least currently, to provide everything in a single product file, so containing all 6 product variables. We use the ESA level 1B as the input, so we have some dependence there upon ESA. And we are, in addition, committed to make the product GHRSST compliant. And in addition, we are coordinating with ESA to ensure that there will be, at least to some extent, a consistency between the ocean and the polar products in order to address the Copernicus user needs. This is to give you an overview of the processing chain as it's currently envisaged. So we basically have, we foresee 3 main steps, being the pre-processing first, which takes the level 1B products and performs various necessary corrections and adjustments that in general are mainly related to salinity retrievals. For example, at the L band, we are very much affected by the galaxy and sun glint contamination, as well as the Faraday rotation in the ionosphere, which is not that relevant for SST at the C and X bands. But we do need to account for the fact that since we have these multiple feed horns per each band, and each feed horn has a different zenith angle, we do need to correct for this because it leads to a striping, since the surface emissivity has an angle dependence. So then in the next step for the resampling, well, it will basically be a Backus-Gilbert or like an optimal interpolation to resample the brightness temperature at level 1B, well, instrument viewing geometry to the level 2 sampling configuration. And in the final step, we perform the retrieval, which will be a optimal estimation concept. And the point here is then to have a, let's call it multi-parameter, multi-frequency, and multi-scale concept, meaning that we use all frequencies at the same time. We retrieve all parameters at the same time with some exceptions. And we also provide each level 2 variable in the resolution based upon the channel that it's most sensitive to that particular variable. And let's see, anything else? Yes, and all of these algorithms are developed by Estellus and Ocean Data Lab. So they are two SMEs from France. And currently the retrieval part is fairly mature, while the pre-processing and resampling are still works in progress. And this is just to highlight a bit or showcase what we have so far in terms of retrievals. Pointing here out that this is all based on simulated data. So this is a test data scene over the Southern Atlantic with the bottom of South America here. And you see here at the bottom in the top panels to the left, you see the reference SST and then the retrieved SST. And at the bottom, we see the theoretical uncertainty of the SST that is provided by the OEM retrieval algorithm. And then to the bottom right, you see the error of the SST. And you can more or less see that there is some sort of matching with the theoretical uncertainty. You see in the warmer water to the north, you have quite, let's say, much lower errors, while at the bottom with the colder waters, we see that it's a bit noisier. And then we also have a subtropical storm here that has some impact as well. And then to the left, to the right, we also see let's say, a statistics over multiple, so in this case, 5 test data scenes in total, where you can see the theoretical uncertainty in the blue line, the dark blue line, and in the light blue line, you see the error standard deviation as a function of the reference SST. And in the dashed line, we have the requirement at 0.2 Kelvin. So, and then the top lines here that I'm trying to highlight here with the laser dot, those are retrievals that are based on the fore and aft views separately. And we can see that while we do meet the requirement, except at colder waters, yeah, so basically the challenge is here the colder waters, and I note here that the polar product has a requirement on 0.3 Kelvin, which takes this into account. But then in the lower lines, we instead use, let's say, a combined retrievals, basically just an average of the fore and aft. And then we see that we do get below the line almost everywhere. But yeah, I point here out that this is simulations. It's a very ideal scenario with, for example, we must here assume that the radiated transfer model is perfect, but there are like no simulated contaminations, for example. So this is still work in progress. So yeah, so I would like to conclude with a bit of an outlook and what the status is right now. So we are currently developing the processing specifications with the current focus on retrievals, as the areas where we are mostly mature, and the pre-processing and resampling scientific ATBDs are under development by Estellus and Ocean Data Lab. And I mentioned or highlight here as well that we, of course, plan to utilize existing tools available at EUMETSAT and infrastructure. So the trusted network of drifters, the CV tool, and the Felix 2 matchup database. For more information on that, I refer to Am's talk yesterday. And I mentioned also that currently the ground segment is under design and development, which will be a joint ground segment with another Copernicus expansion mission, Crystal. And yeah, I would like to finally say that I very much welcome questions, feedback, and suggestions from users. So if you're interested in or planning to use the products, then don't hesitate to reach out to me and other colleagues. And that was all from me. Thank you.
Thanks, Eric. Probably you're in very late already. I don't know if you want to stay a bit longer for the questions of this session.
Of course, the clock
If you
is
can
3
manage
here,
20
but
minutes
I don't
more
mind staying up
in case.
40 minutes more. No problem.
Cool, thanks. And then last one, we have Amy Allerscans on anticipating operational microwave sea surface and sea ice surface temperature products from SIMR and AMSAR 3. Thanks, Amy.
Yes. Good morning, everyone. My name is Amy, and I'm from the Danish Meteorological Institute. So today I will be talking about work I've been doing together with my colleagues at DMI about operational microwave sea surface and sea ice surface temperatures from AMSAR 3 and also from SIMR. So first, I will start with some words about the AMSAR 3 plans we have in OSISAF. So we want to produce near real-time level 2 products of passive microwave-based global SST and IST from AMSAR 3. And the overall plan is to provide SST and IST separately in the beginning, and then during the time frame of the project, we want to investigate the possibility of a continuous and seamless product. And initially, the product will be distributed as a demonstrational product. We will then do a thorough validation, and after 6 months, it will become operational. And I should also say that all products generated will be GHRSST compliant. And then here I'm just listing some expected usage of such a product. So for IST, we can, together with the infrared one, better understand the vertical energy transport in CIS areas. And for microwave SST, we can use that for gap filling of infrared SST datasets. So now I'll just briefly describe the algorithm we're using for the SST retrieval. You can see the flowchart to the left. We have two main components. One is the wind speed algorithm, and the other one is the actual SST algorithm. So the wind speed one, we are using a statistically based model using regression, where we use brightness temperatures and incidence angle as input. So in the first stage, we do an initial estimate of the wind speed, where we use so-called global algorithms. So we have one set of regression coefficients for all retrievals. And then in the second stage, we do another wind speed retrieval, where we use localized algorithms. So for each wind speed bin, we have one set of regression coefficients, and then we get a final wind speed estimate. And we want to use the wind speed because that's as an input to our SST algorithm, which is also a two-stage model based on regression. And here we also make use of localized algorithms. And the idea is then that if we do these localized algorithms, we can somewhat include the nonlinear relationship that we have with brightness temperatures. So in the first stage of the SST algorithm, we do localized algorithms based on fixed latitude intervals. So for each latitude interval, we have one set of regression coefficients. And then in the second stage, we bin based on SST and wind speed. And as input, we are using brightness temperatures from the 6, 10, 18, 23, 36, and 89 gigahertz channels, dual polarization. And then also incidence angle and the wind speed from the wind speed retrieval. And finally, also the relative angle between satellite azimuth angle and wind direction. So because we're using a statistically based model, we need to have some training data to train it on. And we currently do not have a data set for training from AMSAR 3. So we're using AMSAR 2 for the tuning of the algorithm at the moment. And for this, we're using the ESA CCI matchup database, which includes brightness temperatures from AMSAR 2 level 1R that we have made a bias correction to using JAXA provided coefficients. And this has then been matched with in situ observations from drifting buoys and also reanalysis data from ERA 5. And this here just shows the geographical distribution of the matchup we have in the datasets that we're using for training. And here I am showing some preliminary results of SST retrievals from AMSAR 3. So this is for the month of March 2026. And we have retrieved SST using calibrated AMSAR 3 brightness temperatures but with a somewhat simplified algorithm because we have not yet matched the brightness temperature data with auxiliary data, so we don't have the relative angle yet. So that will come later when we have done the matching. And we have applied some basic masking for land and sea ice contamination and also some brightness temperature quality flags. So we're also missing some RFI and rain flagging for this, but this is, as I said, preliminary results, and we will continue to develop the algorithm. So for the next step, we want to tune the SST algorithm using AMSA3 data, and for that we would need a matchup data set. So currently we're thinking about producing a matchup database where we have AMSA3 level 1R brightness temperatures matched with in situ data and also auxiliary data. So when we start to receive the final calibrated AMSA3 data, we will then try to generate such a matchup data sets. And then we also need to do validation. So we want to set up validation processing where we can evaluate the performance of the algorithm. And now I'll be moving on to Simmer. So Simmer is developed by ESA, as you've heard. It has a scheduled launch in 2029, and it will provide high spatial resolution measurements and derived products, 3 of the main ones being sea ice concentration, sea surface temperature, and also sea surface salinity. And the key assets of Simmer for SST monitoring is better spatial resolution at 6.9 to 10.7 gigahertz channels and lower uncertainties, and also improved spatial coverage compared to current infrared satellites. So the Simmer AltoPad is a 4-year project initiated by ESA, where we prepare polar, ocean, and global land level 2 products, and also the ground processing prototype for the Simmer mission. And the DMI is responsible for the sea surface temperature processor, the sea ice surface temperature processor, and also a related processor for lake surface water temperature. So because of the higher resolution, we will be able to retrieve lake surface temperatures as well. And all software, data, and algorithm documentations from Simmer AltoPad will be open. So in particular, the ATPDs and also the level 2 GPP. So we will share the code base and documents on our GitHub page. So make sure to have a look when they become publicly available. And then this is a demonstration of the SST baseline algorithm on Simmer data. So we don't have any actual Simmer data. So this is simulated data. So we have a realistic test scene for a typical polar case in the area around Svalbard and the Barents Sea. So the simulated level 1B data is generated using the SEPS forward instrument simulators. So we have retrievals for forward and backward scan separately, as you can see here in the case. So yeah, this is just to show some preliminary retrievals. It's still a work in process. The project finishes in 2027. And now I'll move on to IST from passive microwave observations. So microwave brightness temperatures at 6.9 gigahertz are highly correlated with subskin IST. That is the temperature under the snow surface. Let's see if I can. No. Yeah. Here. And we are aiming to estimate the snow ice surface temperature, which is the yellow stars from C-band passive micro observations. And currently, operational level 2 products are being developed. So for AMSA3, we're working on in the EUMETSAT OSISAF project. And in the ESA Simmer AltoPad project, we're working on the Simmer. And the target accuracy and performance under freezing conditions is a total standard uncertainty of less than 3 Kelvin at effective resolution of 15 kilometers or less for Simmer. And here I show the monthly IST fields for March 2014. To the left, we have the infrared IST from the DMI level 4 product, and this then represents the snow surface temperature. In the middle, we have the passive microwave IST, and this represents the snow ice interface temperature. And to the right, you see the difference. And their difference resembles the distribution of snow depth on sea ice, and this is then the foundation of a snow depth retrieval algorithm. And then I have a demonstration of the baseline algorithm. So to the right, you show the trajectory map from a drift track over 5 to 6 months. And to the left, you have a figure that shows the time evolution of buoy temperature profiles and emission depth. So using the C-band passive microwave, we want to estimate the snow ice interface temperature. That is the black dotted line you see here. But what we're actually measuring using C-band is the subskin IST. That is the pink line. So this one here. these. So we want to then, in order to get the actual snow ice interface temperature, we want to apply a bias correction method. And for this, we have generated a matchup database of Zimbabwe temperature profiles, which we have matched with AMSR2 brightness temperatures and also reanalysis data from ERA5. So we're currently trying to develop this bias correction method to go from the subskin to the snow ice interface temperature. And then I just want to say a few words about our latest SIMR developments, which is the uncertainty estimation. So we're developing the uncertainty estimation methods together in the SST and IST processors. And we want to go for a Monte Carlo-based simulation approach to derive the total standard uncertainty. But we're going to base it on a lookup table approach for offline Monte Carlo simulations to speed the process up, because the Monte Carlo simulations are quite heavy to run. And a lookup table then would contain the pre-calculated uncertainties based on selected parameters that we have binned over some plausible range. But this may include some physically unrealistic combinations of values. And also because the lookup table size increases with the number of parameters, we want to do a reduction of dimensions. And the idea is then to do a clustering of brightness temperatures. So you see here an example of brightness temperatures, of clustering in brightness temperature space for the 6 GHz channels. For the SST, we would do it multi-frequency space, but that would be quite difficult to visualize. So instead you have this one for 6 GHz channel, which is what we're using for the IST. So the point is then that each cluster would represent a brightness temperature space and with a fixed uncertainty. So instead of using the actual binned brightness temperature, we would use the clustering centers in the lookup table. So when calculating doing the uncertainty estimation, we would then calculate the distance between the actual brightness temperatures for the retrieval and the lookup table clustering centers, and then choose the one that is closest. Yes, and then the last slide. So I just want to say, if you want to know more about the SIMR ATBDs for SST and IST, and also about the uncertainty estimation, you can visit our public ATBDs here. And lastly, I just want to say that we have an update of the ESA CCI version 3 passive microwave SST climate data record for AMSR2. Yeah, that was all for me. Thank you.
Thank you to both speakers. And are there any questions? And maybe preferably start with Robin, if he needs to drop out. Any questions? Robin, are you there? Maybe a question from me?
Yes.
Yeah, I was just wondering, maybe that's a historical, or if you can sum up in a very easy way, why there are two approaches on the algorithms? Why one for polar and one for global ocean?
I mean, this is, I would say, a matter of, what's the word? I mean, ESA, they have procured it's just the different procurements, right? And I think it's a quite advantageous that we have different approaches, because it allows us to have a bit more diversity in the way we approach things. And then we will compare in the common overlapping areas to find the strengths and weaknesses of both approaches. But why we went for both, it's just because it's a separate development between ESA and EUMETSAT, and that's it. So, yeah.
Great, thanks. And it will be very interesting to actually see the results of the comparisons in the overlap areas.
Definitely.
Thanks.
Thank you.
Any more? Do you have any questions for anyone, Robin? If you want to go.
No, I think I'm good. Thank you.
Yeah, we have a question here.
Hi, Robin. You were mentioning about Bristol and CIMR ground segment that they they will be combined. Are there any plans to combine also, products from each of the missions? Because yeah, they are kind of different different parts of this, measuring the same thing. Thanks.
No, the thing is that the crystal, the products that EUMETSAT are developing for crystal is a bit different compared. I mean, it's an altimetry products that we are developing. So this kind of multi-mission product that you're referring to is also not something that EUMETSAT is typically producing. This is something that I would probably see one of the EUMETSAT SAFs doing. But yeah, there's no plans on that from EUMETSAT side, is the summary answer.
Thanks. Are you going back to sleep? If so, have a good night.
I will stick around a little bit, I think.
Okay.
I'm not asleep, actually.
Sure. Okay. If there, yeah, Pia, go ahead.
Well, in that case, Robin, I have another question for you. Pia English from DMI. I'm curious about how dependent the optimal estimation is on your auxiliary information. Do you have any idea of the sensitivity of your retrieved SST?
So what I can say is that from our simulated world, we have done experiments with both using, let's say, auxiliary data from ECMWF, which is basically the same data that we use for the to generate the test data, which Estellus is doing with SEPS. And but they're just perturbing it and then use that as first guess data. And then we have used it as without the auxiliary data. And the results is that Simmer doesn't seem to need to rely that much on auxiliary data. We do see very good results without using first, let's say, a priori data. But of course, this is just the simulated, let's say, very controlled environment.
Thank you very much. That sounds good.
Thank you.
Well, if no more question, yeah, more questions.
Yes, I have a first question for Amy. Thanks a lot for presenting your work. I was wondering if, when you presented the test case in the polar region of retrieved SST, if you are planning also to see the structures in SST gradients.
So we have some, not specifically for the gradients, but we have some reference data that we're comparing against, at least, to see that we get the pattern right and so on. But as we have trained on AMSR2 data, there's quite a difference between the AMSR2 data and the simulated Simmer data, which makes it a bit difficult to compare the results. But yeah, it's a good point. We will take that into consideration. Thanks.
Thank you, Amy. And I have a second question for Fumiaki. Yes, regarding the AMSR CDR. In the beginning, you mentioned you made an assessment of effective spatial resolution through comparison with infrared data. And I was wondering if you could provide us with a bit more details on the assessment methodology. Thanks.
Okay, thank you for the question. It's very simple, and we use the infrared, the high resolution SST data, and we apply the spatial filter to infrared SST maps, and we try to find the best smoothing scale that can produce the AMSR microwave SST maps, and we regard that smoothing scale as a spatial resolution. And we already published the paper, so maybe you are interested in it. Okay.
I have a question for Robin. Still there? Is it Robin or Rowan? Sorry, I've forgotten. Robin, hi. So I noticed that in your retrieval scheme for Simmer, there's two steps. You're doing an optimal interpolation Backus-Gilbert to deal with the overlapping footprints and oversampling and so on. And then you're separately doing a multi-wavelength retrieval. And I just wondered whether anyone has given any thought to doing all this in one step, because it seems to me that you're compounding possible errors when it comes to the spatial properties of the retrieved SST by doing this all in a number of steps.
I mean, the main reason why we are going for this approach is because we do have all these separate variables to generate as well, and we do have these requirements on having what do you call it, like internal self-consistency between the product variables, and this is where the idea to have this multi-parameter optimal estimation framework. But for sure, there is nothing to say that we can assess the impact versus having just a single retrieval chain without, for example, if we would just if we are only retrieving SST, then there's nothing to say that we can just skip the other parameters and then compare with the two approaches, the one that we are doing now and the one that you suggest, as you are, if I understand you correctly.
Well, I don't think it's necessary to have one or the other. I think it's possible to conceive of retrieving multi-parameters across all these wavelengths and across the two-dimensional field in one step. And I think that'd be quite an interesting thing, because I think that would actually be more self-consistent.
Yeah, no, okay, I think I understand your point. The problem is that we have all these requirements are apply at different resolutions. So we have the salinity that is at 60 kilometer, and then we have these atmospheric parameters of precipitation rate, for example, that has a goal resolution at 5 kilometers. Do you understand my point here, or am I misunderstanding you? So this is the reason why we are doing these multiple steps. Basically, it would be like one retrieval performed at the low resolution, one at the mid resolution, which would be the SST, and then one for the high resolution at for the atmospheric parameters that are more reliant on the high resolution, like the K and Ka channels. I'm not sure if I understand exactly what you're suggesting, but I would love to have a chat later if it's possible.
I'd like to talk to you, but that's clarified the motivation. Thank you for that clarification.
Yeah, thank you for your question.
Yeah, okay. One last question, and then we move on to the GHRSST priorities, which I guess also leaves room for questions.
Okay, sorry. I've got a question for Robin. It's not closely related to what your talk was, but from Chris Donlan's talk yesterday, I learned the concept of Simmer companion, which is basically to measure the near surface air temperature and humidity so that you can calculate turbulent heat flux. I was wondering if you can talk more about that, because I might have missed something from Chris Donlan's talk. Is it is it more like a mini satellite, or is it manually controlled remote out vehicles? Can you tell me more about that, please?
From what I understand, it's a mini satellite. I'm not sure exactly what the correct term would be here. But the thing is, I don't know much more than what Craig was telling you yesterday, because I'm not involved in that mission as well. It's a completely on ESA. What I remember is that it's a joint. It's supposed to be a joint development between NASA and ESA, and yeah. But other from what you said, I don't know that much more about that. So sorry about that.
Anyone from the audience that you might?
I could say just a little bit from what I've heard in other meetings. So this is kind of a follow-on. There was a proposal for the butterfly concept. And so this was kind of then a happy medium where then they were taking a CubeSat approach. A lot of the instrument development is Shannon Brown at JPL. And so some additional microwave frequencies to try to do better at the near surface air temperature and humidity aspects. So the idea was that butterfly concept was going to be a super expensive mission concept to try to get the high resolution and these frequencies. And so it's this amazing collaboration here where you've got the simmer instrument that does so much at the high resolution, then they can just have a separate simple instrument to get the frequencies specific to near surface air temperature and humidity. But Shannon Brown, Shell, person at Scripps, so I can pass along some of the more direct contacts.
Thanks, Gary, for the input. And now we can move on to the discussion, although I think this is already part of the discussion, on GHRSST priorities regarding the microwave products. So input, comments, wishes. Where should we go? Christina.
Well, I guess here we should just bring up some of the discussion we did yesterday about maybe the possibility of GHRSST community to ask to JAXA formally the extension of the overlapping period between MCR2 and MCR3. I think we should somehow summarize that this here in this session. I don't know. This is my point here. I don't know.
One obvious reason, I guess, that's already noted is the CDR, the AMSR CDR development. You'd like to have that consistent, and then you'd need a good overlapping period. That's one thing that was brought up also yesterday, I think. That's it. Dalia, please stand up, or just get the microphone.
I think we should consider the advantage that we have now for MCR3 and push for the long-term overlap of the two mission, MCR2 and MCR3, to have sufficient time of continuity of the two missions to make an evaluation of the difference and provide consistency. And I think it will be important also to use MCR3 in preparation SIMRA. So I think these are three important points that GHRSST should address.
So would that be a formal recommendation from the GHRSST community? How would you like that to communicate? Should it be user specific, or do we make a GHRSST statement? Chris, any thoughts on that? On how to?
I think I'm very happy to say that we could coordinate a joint statement of the GHRSST community's opinion on it. If that's a helpful way, Misako,
Yes,
I think we'd be happy to do that. Yeah.
Yeah, and I think that
Me?
it's nice to have the kind of the letter to the JAXAS, the director of my department of the Earth observation, and a letter from the Greece to community. So and mentioning the how important be the continuation of such data and the impact of the if the mission is stopped providing and how long you need it for at least how long you need it for your purposes. So that's kind of the description is with this endorsement letter is quite nice. Yeah.
Okay, well, I think we should take this as a priority. I think the timescale is about a month or two at most. Yes. So I
Yeah.
would ask everyone to be responsive when the GPO asks for their input.
Thanks. Anything else on priorities for passive microwave? Andy? No, I think maybe use a mic for the people online. There's one coming.
Okay, I have a mic. So obviously, unfortunately, I was picking up my post this morning, so I missed a lot. But there's a lot of talk about essentially using optimal estimation and fast radiative transfer. So I wondered what people thought of what is the status of microwave radiative transfer modeling. I see the Gillett SURF-M Ocean paper. I was a referee on it at one point, and it's still in press, apparently. Is that true? I mean, what do we actually think? Do we think that passive microwave RTM is good to go now? Are we happy with it? I remember Shell a long time ago saying it's just hard to beat regression, but now the performance of these algorithms seems to be substantially better than regression-based retrieval. So do we think that passive microwave RTM is good to go now? Some sort of statement from some people who do this stuff would be great at this point.
Well, I hesitate to put you on the spot, but what you missed earlier, Andy, was that there'd been some work calibrating, so to speak, the brightness temperatures of the AMSR2 and against VIIRS infrared, and that seems a way forward to me to try to constrain this at least in a self-consistent way that you can then use the same model. And if you're self-consistent, you in some senses you're accounting for. Wait, if you cross-calibrate using a model and then you retrieve using that same model, then you're achieving a self-consistency. But it's not necessarily saying you've got the physics exactly right, but at least it's going to be consistent. So I think this work is interesting. But if you want to say more about it, Yukio.
I mean, would you call that like a radiated sparse correction then, sort of? Kind of. Okay, so that means the models are not actually off the shelf ready to go now, or does it? Okay. Watch this space then. I'll talk to you, Yukio.
Another possible issue we should think about is we have a number of SIMR and AMSR3 products planned and coming together from different agencies. So I guess the intercomparison task team might want to look quite carefully at these because this is the way in which we learn from each other and learn what the strengths of the different approaches are. So maybe we should start thinking about that for AMSR3. It's very timely.
For the next GRIS meeting, there could already be something there.
Is it working? So just following up, I think we will discuss this issue within the intercomparison task team and see what we can do to contribute for this. Christina.
Of course, we can do it, but I think it was a level 4 intercomparison team. So I think it's out of, maybe we could consider of, I'm completely, I mean, I do agree that we should do that, but I don't think it's on our roof, even if we can contribute. But if anyone in the audience willing to lead a task team on that, and I would say, I would suggest that some of the presenters that today have presented I would suggest and I would encourage both as a chair of the intercomparison level 4 task team and as GPO, I would suggest that we address this point by creating and we can contribute and we can help for sure. Daniele, Jorge, and me, I'm pretty sure that we can. But I would ask someone of the speakers to lead that. And I think it would be, I do agree, it's really interesting and we should do that.
And just to provide a very quick follow-up, I would say, to me, this looks like a natural extension of some ongoing tasks already in the ICTT. And in particular, I'm referring to the merging of infrared and microwave, which was also mentioned by Amy, if I'm correct, on the use of passive microwave for IR gap filling. So answer 3 would enter into this ongoing task. But of course, creating a new one
someone from HAXA
would require some help.
I don't know, I can't remember the task teams by heart, but is there time now for a passive microwave task team again? Is there something to look into? There's Simmer coming up, we have AMSAR 3, there's suddenly the passive microwave community is active again, new things are coming up. Maybe a task team on that only is something we could think of, and they could address more specific issues, the comparison of different products, various activities that will kind of naturally come up now that we've got AMSAR 3 and Simmer soon. Maybe that's something to think of.
Completely agree. We just need volunteers. So I'm not looking at anyone, but yeah.
Thank you for the proposal. Maybe not thank you for that. Yeah, but yeah, of course, we are really wanted to know the these differences between the AMSA 3 product in each agency. So I think that that could be nice to have such kind of the task team. But I think that it could be quite dedicated, not a kind of the task team. So I think that also the small group with the who are interested in producing the AMSA 3 data from SST from AMSA 3 data. So maybe gathering together and have this small discussion and a way to compare in a to establish the validation, same validation method and the same validation data set, and maybe the target period. So that such kind of things can be done, and I can arrange with my Japanese colleagues to make such kind of the opportunity. But I'm not sure how many the people from the other agencies want to join. So maybe the ask the GPO or the others to make a call for the who are interested in such kind of the activity. So maybe within a year or maybe 1 year or 2 years, because the data is just released at the end of this month. So I think that some of the people needed more time for the preparation. So maybe the 1 year or 2 year terms could be nice to have such kind of the activity. Yeah.
Maybe it's already a good idea to find a few people here that are interested in working in this. And I think it doesn't have to be big. It's on, right? Yeah. And of course, activities can start later on after the end of this month. But it's also good, even if it's a short-lived task team, it's also good to show that GHRSST is actively looking into things like that. It's also good a good argument for agencies to see that there is activity on such issues. So I'm sure there's people around here that now that are interested in participating, and it doesn't have to start now, but just to think about it and plan for it. Thanks. Yeah, Jorge? And then Rosalia? Jorge, will you use the microphone?
Oh, thank you. It's just a quick reminder that, you know, the dates for the decommissioning of MODIS are coming up very, very soon. We're not far away, kind of 6 months from that. So I really think the whole issue of VIIRS needs to be a real top priority right now. There's so many people that use MODIS, I think, in optimally interpolated data sets. I don't think this is going to be a trivial, in my humble opinion, it's going to be a trivial transition. So anyway, thank you.
And last input, Rosalia, maybe? And then we break for coffee.
I was thinking, respect to what was discussed with this group of microwave. Perhaps it's true that we need at least a period in which answer 3 is available to start the activity, but perhaps between now and the next Greece meeting, we can start to discuss what should be the items to identify the items that should be addressed by this group, and then if we are ready to that before the next Greece meeting, perhaps we can start the real activity. Otherwise, we can start the activity later on. But I think it will be very important now that we have a better. It seems from your presentation that the quality of the data is much more improved, and we are planning to have a new mission on microwave with higher resolution. To start the activity I think is mandatory, and also to maintain a record of the microwave measurements for long-term record, and make intercomparison with the similar record on infrared will be an important point to consider here. So if we want to establish, even if I'm not a microwave expert, I could try to contribute to this thing.
Excellent. So volunteers needed. Please talk to each other. And with that, thanks for the first session of today. Thank you to all the speakers. Let's one round of applause again, and coffee.
I don't know which one is to delete. And also because we wanted to display until when is the break room, but I don't know how to delete from here.
When we started.
So I would say at 11:05. Yeah, like 15 minutes break.
Yep.
This is first. So where do you delete?
In the backspace.
Backspace. Okay.
And I think that I haven't downloaded
the next one. So it's from
session 2.
Sessions 2 and 6. Right now it will be 6 first and then 2.
6.
But well, it will go in tandem, both of them. Yeah, this one. Yeah, this one. If not, I have the pen drives. But I have saved the pen drive. So because I have all other
You downloaded?
Yes.
All right.
Yes.
Okay.
Right,
That'd be easier.
Yeah, it's easier because I have all for today. At least this.
Okay. And yeah, this is
Yes.
right, and then this is section 1, 6, 6. It's uploaded, so maybe I know this one.
Yeah, Tuesday is
All right, so we will refresh this one.
Yes, we will need to edit that one.
Then, section 2.
Yes.
Okay.
And also a video in case Marisol is not present.
Okay, I see.
Yeah.
Do you get any email from the Chris?
No.
From
Cristo, no.
And because he was absent.
Yes.
Yesterday.
You
haven't heard from him?
No. Perhaps I can write to him to see.
I think everything is covered, I think.
Yes.
Right, and also the section 3.
Yeah, same.
Yeah.
¿Qué tal? Sí, está aquí. Ahora si quieres la vemos.
Creo que hay un typo, pero bueno.
Sí, pues buscarlo ahora.
Bueno, eso es un PDF, así que.
Vale, sí.
Iremos con él. Pero creo que está en el nuevo y no en el viejo.
Sí, este es el nuevo que hay aquí.
Vale, no, porque ¿dónde cambios? Bueno, sí, es que lo.
Sí, o sea, me llamo por si acaso. Sí, por si acaso, porque luego. Mira, digo, solo por si acaso, porque luego tengo 15 presentaciones y.
A ver.
Control de varios, si quieres hacer.
Vale, sí, es la nueva.
Sí.
Y a ver. Bueno, venga. Vale, merci.
Nada.
Gracias,
Nada más.
Yeah.
Okay.
Something.
Yeah, I'll just welcome back. So everyone, welcome to session 6, which is satellite SST for numerical weather prediction, ocean modeling, reanalysis, and climate models. That better? Okay, so our keynote speaker is Sean Oshie, talking about LETKF-based ocean research analysis for quasi-global domain.
Thank you, Chairman. I'm Shinoishi, research scientist at Riken, Japan. So today I would like to introduce the reanalysis, the research analysis dataset recently I created. But I would like to start a very, very basic knowledge about the data assimilation because the Kachi-san asked me to start at this point. So I think I do not need to introduce the ocean observations, but I would like to demonstrate, say that the important things in the ocean observation is that we cannot accurately represent or reproduce the three-dimensional ocean because, especially because the algo profiling float has a ratio of the one profiling float per the 300 kilometer by the 300 kilometer. But the ocean eddy has a radius of the 100 kilometers approximately. So we cannot reproduce the three-dimensional oceans. So some of you might think about how about the simulations. So let me start to talk about using the very, very simple model of the Lorentz 63 with the 3 variables. So this movie shows the X and Z dimensions of these toy models. So these toy models are going to the left and right side randomly because of the chaotic natures. But oh. Okay. Not working on online? Ah, okay. Zoom is down now. We need to wait a moment to restart the Zoom.
小野さん。ズームがおかしいというか。
Okay, so please enjoy this movie of the going to the left and right. And I would like to go to the next because of this is more interesting.
Okay, in the meantime, I have an announcement to make to you. I don't know what do you think if we were thinking about sharing the list of attendance. We will send an email to the people at home because they cannot hear that at this moment to publish the list of attendance and the email to facilitate the collaboration, so you can contact each other if you want. So if anyone has a problem with that, I don't want to share his personal data or his email, please let us know and we will let him head out of the list. But otherwise, if we don't receive any constraints, we will publish the list in the Moodle by tomorrow morning. Okay, so like that you can contact anyone if you wish. Is that clear? We will send an email for people at home as well when we have connection back. Okay, we will remember you this tomorrow. Okay. Anyone has anything to announce, to explain? You can come here. Meanwhile.
Okay.
One question, how many of you do you have EduRoam connection right now? The ones that you are, so the people in the room have Wi-Fi connection. Everyone, okay, so okay.
Okay, let's restart. Resume my presentations. So you can understand these movies. A lot of time to see this movie, but I would like to say, even if we created a very accurate simulations, but if we add we never know the true values. So to imitate these situations, I add a very small noises to the initial conditions. So the errors are grown over the time. So over the time, so we can see that these 2 points, the black and red, tend to be the different state. So this movie indicated that simulation cannot reproduce perfectly the real oceans. So therefore, we use data simulation to connect or combine the simulation and observations. As I indicated, the simulation provide a three-dimensional homogeneous output, but the simulation becomes more less accurate. On the other hand, observation provide fine spatial, temporal, and more accurate values, but the observation contains the missing values in some pair. The data simulation combines these two, the simulation and observations, using the statistical method and the dynamical systems theory, and provide a more accurate data set without missing values, which is called either analysis or the reanalysis. So this table summarizes a global reanalysis dataset and high-resolution regional reanalysis dataset in the Pacific regions for each data simulation method, 3D bar, 4D bar, Kalman filter, and ensemble Kalman filter. The left-hand side, the variational method is based on the Bayesian estimations and commonly used in the ocean data simulation community. On the other hand, the ensemble Kalman filter is rarely used. However, the ensemble Kalman filter has the advantages of being easy to implement various models, but there are only one option, the p-orders. But this dataset is unfortunately currently not available. So we can say that there are no ensemble Kalman filter based ocean nearest datasets now. So let me talk about introduce what the ensemble Kalman filter is. And here we assume that we have 5 ensemble members, and we estimate the uncertainty in the simulations using this ensemble spread. And then we conduct ensemble simulations, and we get forecast the output values from the simulations. And generally, the errors are grown. The forecast error, the forecast spread becomes larger than the previous steps. And here we assume that the observation has the same uncertainty as the forecast. So we can easily imagine that the analysis is located at the center or the middle of the observation and forecast. And then we, at the next time step, we again conduct the ensemble simulation. So this is a simulation cycle in the ensemble Kalman filter. But generally, the observation has more accurate than the forecast, so the analysis is located more close to the observations. But some observations, such as satellite salinity, might have a very large uncertainty. In such a case, the analysis is located more close to the forecast simulations. So here I talk about the one-to-one assimilation. That is that, for example, the temperature variables is updated by the temperature assimilations. But ensemble Kalman filter can update different variables. For example, if the first member has a higher temperature and higher salinity, and the last member has a lower temperature and lower salinity, it means that the ensemble correlation is positive. In this case, so if the temperature is updated to the higher temperature side, so we can use this correlation information and we can update the salinity to the higher salinity side at the same time. So this is a positive correlation case. But if the correlation is negative, the temperature is updated to the higher temperature side, the salinity becomes lower. So this is like a schematic figures what the ensemble Kalman filter works. So again, we go back to the motivation of my studies. So there are no ensemble Kalman filter-based ocean research analysis, although it has the advantage of being easy to implement with the various models. And I'm now involved in the JAXA project, and JAXA asks me to assimilate a geostationary satellite, Himari 8 and Himari 9, which provide a very fine and fine spatial and temporal observations in the Pacific and Indian Oceans. So therefore, we motivate to assimilate the very fine, the frequent the observations. But the frequent data assimilation is a challenging topic because the analysis field contains a dynamical imbalance. In the conventional data assimilation systems adapt a relatively longer assimilation cycle. So if just after the restart of the simulation, the initial shocks is generated because of the dynamical imbalance, but this negative effects will be dissipated over these long simulations. But if we change the data assimilation interval is too short, such as a 1 day interval, so the negative effects of this initial shocks is accumulated, and some systems might break the basic field. So I would like to show this example, but before going to that, I would like to introduce my systems roughly. My system is based on the ocean model from the POM model and data assimilation from the LTTF, which is one of the ensemble Kalman filter. And we assimilate typical observations, the sea surface temperature, salinity, and sea surface height, and in situ temperature and salinity at a 1 day assimilation cycle. So this is the first figure just after I started to construct data assimilation systems. The top panel indicates the sea surface height field in the analysis field in the abyssal. So you can easily find that the data assimilation system cannot reproduce the basic state of the sea surface height, especially around the Kuroshio extension regions. And I also found that there are unrealistic values exist in the distributed in the sea bottom. So after the 4 months later, after I studied these systems, the sea bottom salinity reaches to the 68 PSU. So this is the world record of the over the global oceans. To mitigate, so these the negative effects or the unrealistic values is coming from the initial shocks. So to mitigate these problems, I explore an optimal setting for frequent data assimilation, and I found that the most suitable setting scheme is a combination of the additive inflation, RTPP, IAU, and AOEI. So this is a method of the data assimilation, and I would like to skip this. This is because of the too detailed for the outside of the data assimilation researchers. So after I found these schemes, so I created the ensemble Kalman filter-based ocean research analysis dataset called the LoRa, configured for the Western North Pacific and maritime content regions, and I compared the validation result with the existing 3D bar-based reanalysis dataset, Jacob2M, which is developed by the GHRSST, Japan. And this is a validation result of the LoRa version 1.0. So we first calculate RMSD relative to the reference data such as the drifter buoys and Himalaya. And we can take differences of these RMSDs between the Jacob2M and LoRa and normalize by the RMSD by the of the LoRa. So red color indicates the LoRa is better, and blue color indicates the Jacob2M is better. In the sea surface current field, the LoRa has more accurate values compared with the Jacob2M. In the mid-latitude region, especially under Kuroshio and Kuroshio extension regions, but in the subtropical region, Jacob2M is better. In the sea surface temperature field, so LoRa has more accurate values compared with the Jacob2M. So we can say that LoRa has a sufficient accuracy for geoscience researches and various applications. So this dataset is released by the JAXA Riken Ocean Analysis website. So if you Google the JAXA Riken Ocean, so you can easily find this website. So let me show the example of the snapshot. This is the temperature of the at the sea surface, 400-meter depth, and salinity at the sea surface, and ocean current at the sea surface. So you can easily change this snapshot by changing this table in the located at the top left side. So let me say about the advantages of this data set. So LoRa is the first product based on the ensemble Kalman filter configured for the Pacific regions. But the version 1.0 has a limitation of the period and domain. The domain is limited to the Western North Pacific and maritime continent regions, and the period is limited to the after the August 2015. So this is not suitable for the ocean researches because the ocean has a long time scale. So we decided to construct a version 2.0 configured for the quasi global domain and Pacific regions since 2002. The blue boxes indicate the North Pacific region with a horizontal resolution of the 0.10, the eddy resolving resolutions, and the green line indicate the quasi global domains with the 0.25 degree horizontal resolution, that is eddy permitting resolutions. And we integrated these systems since 2002, assimilating the microwave satellite, AMSAR-E and AMSAR-2, and also the WindSat, because there is a gap between the AMSAR-E and AMSAR-2. The WindSat can fill in the gap of these two satellites. And I also validate my dataset LoRa against the GHRSST version 4 from the Mercator Oceans and ORICE-5 from the ECMWF and CGROS from the CMCC. So I choose these three datasets because of these three has almost same domain resolution and output interval. So this is the result of the validation of the sea surface current. So first, I calculated the RMSD over the spatial and temporal. I calculate RMSD average over the space and time. And LoRa QZ has a second most accurate accuracy among these four reanalysis products. I also calculate RMSD ratio of the each data set. So again, the red color indicates the LoRa QZ is better, and the blue color indicates the LoRa QZ is worse. So you can see that the GLORIS 2 version 4 from the Mercator Ocean has a better accuracy over the entire domain. But against to the ORS5 and the SIGGROSS version 7, so we can see that the LoRa QZ is better than these two reanalysis products over the entire domain. So I also calculate the RMSD of the sea surface temperatures. So you can see that LoRa QZ has the highest accuracy among these reanalysis products. So especially around the ACC and western boundary currents, the LoRa QZ has a better accuracy. So I conducted such validations using the different independent data sets, such as tidal gauge and QOV located south of the cross-yaw extension, and Papa V located at the northeastern Pacific regions. And and I summarized these results using the radar chart. The black line indicates the accuracy is the same as the LoRa QZ. The inside of this black line, the LoRa QZ is worse. And outside of this black circle, the LoRa QZ is better. So you can see that the GLORIS is the highest accuracy among these four products. And but LoRa QZ would be the second most accurate data set. And ORS5 and SIGGROSS is a worse accuracy compared with the LoRa QZ. So we are now planning to release this data set in this physical year. So finally, I would like to conclude my data set. The advantage of my data set, the LoRa version 2.0 would be the first reanalysis data set configured for the quasi global domains. And this systems assimilate all typical observations, the sea surface temperatures, salinity, height, and in situ temperature and salinity at a short data assimilation interval. So that is my talk. Thank you.
Thank you. Do we have any questions for Sean quickly? Well, if not, I have one. With the observations, you use the sea surface temperature. Now in our ESA climate change initiative products, can you hear me now? Yeah. So in the ESA CCI data, we provide uncertainties, multiple uncertainties. They've got an independent one, a locally correlated, and a systematic. And most of our users don't use the separate ones at the moment. Would you be able to use those in your assimilation?
For the sea surface temperatures?
Yeah.
I didn't use this uncertainty included in the sea surface temperature observation dataset, but I could. But I would like to note that the observation errors used in the data assimilation include the measurement errors and representation errors.
Oh, okay.
So the measurement errors is such a errors included in the in the observational data set, but there is a difference between the real and the model world. So that is the continuity or the discontinuity systems. So we need to consider, take into account of the representation errors in the observation errors. So there is some statistical method to estimate this representation observation errors included in the both the measurement and representation errors. But if we use this statistical method, so we do not need to use the measurement errors estimated from the observation side. So this is like the gaps between the data simulation side and observation side. So this is my opinion.
Yeah, okay, thank you. Any other questions?
Okay.
Sorry for that. So thank you very much for your presentation, and indeed for a non-expert, I finally kind of understood what a Kalman filter does. So thank you very much. It was really illustrative. Could you just come back to the slides where you compare the RMS? I think it was. I don't remember. I think it was one. So there was one. So my question was, there was one you comparing with Glories and. So your analysis was performing better than ORAS, but I think it was when you were comparing with the SST. I don't remember now.
No, for the SST or the surface current.
So can you? I will, when I see the figure, I will I will see which one
So
I was referring.
go back.
That one.
That one. Okay.
That one for me is kind of so. Here you were comparing. It was zonal velocity. Is that I was not able. I mean, to see which one. So for me here, what is quite astonishing is that when you compare with Glories, you are not performing, you are doing worst, but you are you are doing a great work with ORAS and Glories. No, when both?
The left top side is a compare between the Glories and Roller QT.
Yeah.
And the left bottom is a compare between the comparison between the ORIS-5 and Roller QT, and the right is SIGROS and Roller QT. So again, the red color is the Roller QT is better,
Yeah.
and only the Glories show the better accuracy than the Roller.
Yeah.
But the other two doesn't show such a signals.
So my question was if you could provide more details in the difference between Glories, I mean the one that you are comparing above, and the other two. So they are kind of doing an assimilation using different techniques, or the forcing, atmospheric forcing is different. I don't know if you could provide more information on that.
I think that the Glories, ORIS-5 and SIGROS is based on the same model and the same atmospheric forcing, but the main difference is the data assimilation techniques. So the ORIS-5 and SIGROS adapt the 3D bar, but the Glories and Roller is based on the ensemble Kalman filter. So which is the main difference between these left and right hand side. So and 3D bars assumes that the forecast errors, the simulation errors is fixed over the times. But in the Glories and Roller can estimate the forecast errors, forecast uncertainty in time and space. So this is the main difference between these two sides. So as I show the schematic figure of the first part, so the ensemble Kalman filter can estimate that these forecast errors in dynamically. So this provides a more realistic uncertainty in these simulations.
Okay, thank you. And then just a suggestion, if you are using satellite data from SMOS, I would just suggest to skip 2010 and just begin from 2011, because there was a lot of RFI, especially in the Pacific.
Okay, thank you. This is a very helpful information for me.
Okay, thank you. Given our technical difficulties, I think we'd better move on to the discussions on priorities. Yeah, you're free to go now. So do you have any comments or suggestions for our GHRSST priorities in session 6 for NWP motion analysis? If that's none at all, we might actually be back on schedule. Oh, no.
I do have some information that might be interesting to some people if they're interested in the diurnal cycle of the ocean. In that, as you mentioned, I think yesterday, Owen, that for the ERA 6 reanalysis, which has started production at ECMWF, the sea surface temperature boundary is being done a different way to in ERA 5. And what they've done is take Owen's CCI product as a daily constraint for the ORA6 model. And then I think it's HADIST earlier than the CCI product. And then they've forced it with an atmosphere to create a diurnal cycle on top of this. So the eSIM-WF SST in Euro 6 is going to be an hourly SST with a diurnal cycle on it, which looks quite realistic. So this is a very, it will be very attractive to users on all time scales, I suspect. And I think it's an interesting way of adding all this additional model constrained diurnal variability to an observational product. I think it will possibly, in one sense, is going to lead to users perhaps not going to the observations quite so often, because already people download Euro 5 SST and treat it as if it's a coherent observational data set, which it isn't really. So this is an issue for us as well. But I thought I'd mention that in the NWP world, this is happening.
So I was not completely aware of that. So what you were saying is that in ERA 6, they will use CCI. So instead of HAT, ISST, and OSTIA, because now they were using OSTIA.
Yeah, it's CCI for the period where there's a stable CCI data set at the time they started.
From the 80s.
It's HADIST, the next generation of HADIST, which is consistent with CCI in the sense that the new HADIST version has been built from EOFs that were based on CCI.
Okay.
To project it back on the centennial scale.
Okay.
So the previous decades, earlier than 1980, when CCI starts, will be HADIST. And then operationally, I assume it's going to be OSTIA. When it's running forward. But I don't know that. I'm not sure about that bit.
Okay, because then we will see. I mean, for me, one of the priorities would be, I think it's a risk that the users assume that ERA 5 is an observational data set, that they take it and they don't even know that satellite exists, because when I go to the EGU and I go to some of the sessions for climate, for instance, they are taking ERA 5 SST as an observational, and then Ruben will show you what's the problem with this data set and when you take that into consideration. And another issue that you were mentioning regarding, and I think it is the way, I mean, we are doing a lot of effort in estimating uncertainties, and I'm not sure that the climate and the modelers are using this field. So it would be two things. How do we do for reaching more the community of the modeling and climate studies community to begin to use the satellite data? I mean, at least in the era that we have the satellite data, that's one thing. And the other thing is how do we encourage the modelers to use the uncertainties as well, or to include these uncertainties? And then there is another, because I'm involved in another project for ISA, for CCI ISA. So we tend to give our satellite data in a regular grid, which is great, and it's, but then modelers, they use this kind of grids, and especially, I don't know, ORCA, that is kind of deformating. And here we are doing a lot of work, and we are showing that we need to be carefully on how we regrid because we are introducing artifacts in the regridding process. And I think that there are a few things that we need to take into account and be careful, and I don't know how to deal with all of these things.
Chris?
I think those are good points, Christina. And so two things. There is an ESA project, ESO for Klima, which is addressing some aspects of how to get observational data sets more directly comparable with models. And for example, taking the SST with its diurnal cycle, sampling it as if by satellite, and then how that translates into what the modelers would want, which is the full monthly average over all time steps, and looking at that translation. So I think we have support, a small amount of support to help try and bridge this gap. And the other thing is that there is, I think, Owen, you might say more about this at some point, there is this initiative to develop uncertainty conventions, or the CF convention, so which the modelers use, which are, so this would bring the observational uncertainty into the CF convention world, which I think is also going to reduce the barriers. But I think more will be said about that in another session.
Yeah, I mean, basically everyone, well, even the people who do provide uncertainties, everyone does it in a different format or a different way. So on Thursday, I'll tell you all about metadata and trying to be consistent in how we represent uncertainties to not just in observations, but modeling, and trying to pass them back and forth between each other.
Perhaps on this type of discussion, I can provide my expertise on building the Copernicus Marine Service and the work that we did at CNR to develop SST product specifically for data assimilation on the Mediterranean seas. This type of things will require a continuous discussion with the modelers that assimilate the data, because what we need to be provide to them is something that don't produce shock in the model assimilations, okay? Explain them what we are giving them in terms of accuracy. For example, Chris was saying the importance to have the diurnal variability. At CNR produced for Siemens a diurnal product of SST appositely for data assimilation of the Mediterranean modeling. And at the present, this is still not assimilated operationally, because they try to test the assimilation of the diurnal cycle of temperature observed by satellite, and they have an issue because the parameterization of the scheme at the surface was not inside the model. So after we lost a lot of time to develop a product for them, the product is still not assimilated, is only used for evaluation purpose. Coming on this aim, I think there is also a consideration respect to the previous presentation on evaluation of the model part that obviously depends in which it was shown the differences between the outcome of the Copernicus Marine Service product that is widely used by the community respect to the new methodology. And first, I was not surprised that the Gloria was working so well. And obviously, the difference that was shown is that the Mercator model was better for providing the currents, better result in currents, have a little bit lower accuracy in providing temperature. But this means this is also due to the fact that the methodology, the assimilation, and also the push in terms of assimilation accuracy they want to reach. The model is the outcome of the Mercator model is often used for application on dispersion. So the accuracy of current is essential for them, okay? So it is very difficult to make this type of assessment, especially at the global scale. It's a complicated part because perhaps in some region was better one things and the other region. And a big issue, I think, is the transfer of information that we could provide as satellite towards the depth. That is another crucial point.
Okay, thank you. I think we'd better move on to the next session. Otherwise, we're going to be very late for lunch. So before that, can we thank our speaker again?
So we now move on to session number, well, it's officially session number, I can't read that, it's too small. 2, yes. Yes, it's the eyes are deteriorating. But our first speaker is Pallavi, and it's a session on marine heat waves. So it will be running up until lunchtime and also when we return.
Thanks, Chris. So I am Pallavi Goveka from the Satellite Science team in the research program of the Bureau of Meteorology. So today I'm going to talk about the marine heat wave related work we are doing in the observation and prediction part of it in the Bureau. So I would like to acknowledge my co-authors from the Bureau of Meteorology and Australian Ocean Data Network here. So because this is first talk on MHW here, I'm just going to introduce the definition. So the prolonged period of abnormal temperature is called as a marine heat waves, and we use the marine heat wave. So we use the Hopday definition of marine heat waves for all this work. Hopday define marine heat wave as locations where an upper locally determined threshold relative to the local term climatology is exceeded for at least 5-day period with no more than 2 below threshold days. And then they further categorize it according to how the temperature is deviated from the climatology, how far the difference is. So those categories are from strong, moderate marine heat wave categories to extreme marine heat wave conditions. So with marine heat wave impacts, we do see the thermal stress, and with that we see the effects on fish. So fish kills reporting, harmful algae blooms, coral bleachings, all these impacts are there. And then those impacts further have the operational impacts like fishery closure, changing fishery yields, poor fish quality, shellfish toxicity, that kind of things, and that has the loss of iconic species, human health impacts. So there are social, community, and industry impacts on those of those marine heat waves. So in 24-25 in the Australian region, that summer we had really extreme temperatures around Australia, and it is first time we had the bleaching occurring both of the east and west coast of Australia. So in GBR we had, GBR is the Great Barrier Reef. We had bleaching events in the western side on Ningaloo Reef. There were a report of severe bleaching, fish kills, and in the South Australian region, we had the algae blooms. So it was big topic in media that time with that algae blooms. There were fish kills, reduced fish. Some of the species like Spanish mackerels and tunas were found way south, which is not their usual habitat. Around Tasmania, again, algae blooms, less number of penguins were sighted. So whole of the Australian coast was affected with that marine heat waves. So for now, the current marine heatwave research includes studies on historical patterns, atmosphere and ocean processes, climate drivers, impacts, monitoring, communication and forecasting, collectively providing a rich pool of information for researchers and managers. And for now, Australian users have access to these different tools for tracking daily marine heatwave conditions. So left-hand side, first one is the IMOS ocean current. So this website provides SST anomalies and percentiles using the multi-sensor 2-kilometer SST product, and then the STARS climatology that was calculated using 1992 to 2016 period. And then also the time series for any particular location is available from there for users going back to 1992. Bureau provides weekly and monthly SST anomaly products. They are calculated using level 4 RAMSA-CAMSA products and CCR climatology. There is a marine heatwave tracker that uses the OISST product, and then the climatology, 2 different time climatological periods, and then again NOAA Coral Reef Watch on 5-kilometer product. The climatology is again different to other products. So all these tools are available for users, but the thing is every tool is providing different kind of information. Time and space resolution is totally different. Even in the bureau, we have 2 different products, and then we get to ask from users why this point is showing 2-degree difference, whereas this other product is showing 2.5 degree difference. That sort of questions we always have to face there, and that's because we are using 2 different climatologies for those 2 products. So consistency is issue for the users. Last year, we worked under IMOS and AODN for getting OSTEM together. So with the OSTEM, we are trying to get everything consistent with space and time resolution. So it is 2-kilometer SST anomaly, degree heating day. So degree heating day is giving the indication of how much heat is accumulating in the region. So it is accumulation of positive anomalies, and we are still trying to tune that definition, but this is what we have existent. Degree heating day count, so that is how many days contributed to that accumulated heats, and then marine heat wave and marine cold space categories defined using Hop-Day definitions. And all these informations is displayed through IMOS Live. So IMOS Live here, because IMOS is an integrated marine observation system in Australia, and they are collecting from satellite to all in situ observations, and AODN is a space where everything they are trying to make public available. So here is a snapshot showing the degree heating dates in I think it is 13th April 2026. Sorry, I forgot to put the date over there. So how the heat is accumulating around the Australian coast, and here particularly New South Wales region, we can see heat is accumulating in that region. Those blue spot over the coast is showing where the in situ data is available. So because marine heat waves not only happens at the surface, people are interested in subsurface also, because the species and everything is getting affected over there. So these in situ data, if there are some of the loggers and then gliders, they are providing three-dimensional structure of temperatures. So this all information together is very useful for users. So with the OSTEM, the first challenge, because these are done with the level 3S product, where there is a cloud with the infrared channels, we have gaps. So filling those gaps is a challenge for us. And to that, the one approach we are using to fill those gaps is a mosaic technique. So what we do is, if there is no data for any pixel for today, we go back and we check yesterday. And if there is a data from yesterday, we fill that in. And that way, so the lower, those lower panels are showing 1 day and 14 days SST. So 14 days SST is that the filled up. So we go 13 days back and fill up those gaps like that. And the right-hand side panel is showing different L3S products. So the upper panel over there is showing multi-sensor product only made with the infrared channels from the polar orbiters. And then the lower panel is showing when we add Himawari to it, it is getting more contemporary data. And so blue color means it is more recent data. So we want to see more blue color in these plots, how back we had to go for this. So in the upper panel, we can see some black color over there for the February 14th February 2020, and that was the passage of the cyclone. But when we add into the Himawari 8, we don't see that much black over there. So that means it is giving us more and more contemporary data, but still we want to see how accurate when we go 14 days back. Is it warm bias or cold bias? And we are looking at here. So on x-axis, it is showing number of days without SST. So how long we had to go for. And then the upper panel is showing the mean difference, and the lower panel is showing the standard deviation. So instead of putting SST as it is in the filling gaps, if we were correcting that SST, that could benefit. So that is the one approach we are thinking to try. So this is very initial work, but then we with all this analysis, we found that if we are correcting SST with 0.0253 on average, we should be better off, but then more analysis is needed for this approach. The other thing is getting more and more real data from the satellites, of course. So first panel is showing AVHRR and VS, that is 2 VS, NOVA 20 and NPP, and METOP B and METOP C. When we add Himawari 8, on average, we get 20% more data, but still there are gaps. So now we are we are thinking about adding EMSA to it. And here is an example with EMSA2. So, but then because infrared channels and microwave channels, different uncertainty and everything, we don't want to use the same method. So with the infrared channels, we are using equal area weighted coverage, equal area weighted average for the composition. But with the EMSA, we want to bias correct for all those cloud spills that still there with our retrieving process to correct with EMSA. And also if there is no data at all, we will put EMSA data there. But with the L2P flags and quality, we will make sure that users get that information that this data is coming from microwave. So that is ongoing work we are trying to do. Now to prediction part. So we have GHRSST model running in the bureau. It is a coupled model, and on the 19th, 99 unstable mean, we predict subseasonal to seasonal marine heatwave forecast for up to 6 months ahead. For that, we use climatology 1981 to 2018, and it is a probabilistic forecast products. We do have weekly, fortnightly, monthly, and seasonal predictions, marine heatwave categories, and likelihood that is calculated using the predicted SSTs. And these predictions are done on surface and subsurface at 300 meters down also. And the picture is showing example of marine heatwave categories predicted. So here is one example. So we have SST anomaly, marine heatwave likelihood is given, and also the skills, what are the skills of the model, that is also made public. And then heat content at 300, that is also shown along with the marine heatwave categories. So again, going back to that case study for the 24-25 Australian summer, this is how the prediction. So the last column is showing the observations, actually what happened, and then the first column is showing what our model was showing 3 months before, and then the second column is showing second month, and then the first month. So overall, the area is correctly identified with the marine heatwave conditions, but then the intensity is not right. It is underestimated with the model. And then because users are also interested in the subsurface observations, we are putting our observations and forecast information, whatever we are getting out, together to sample marine heat waves with gliders. So every month, there is a group in Australia where we have scientists and then the fishery people and then government, different agencies, all people interested in this surface temperature. We come together and we discuss the current observations and forecast, and then we decide where we would like to sample with the glider. And there are about 8 to 9 glider missions we do focused on these marine heatwave conditions. So these are targeted in situ observations of marine heatwaves. rapid response deployments. We are doing this since 2018, all Australia-wide events. And then for the monthly risk assessment, we use the observations of SST anomalies, surface heat content, and marine heat wave risk indicators from our predictions. And all these samplings prioritized by intensity, duration, and impact. And then all this information is available public with the IMAS ocean current. So for every mission that we do with the glider, what was the track and what was the observations noted with those missions are made public. So we are doing with the OSTEM, we are providing the thermal stress and marine heat wave monitoring metrics at very high spatial resolution. And we are trying to tune now those observations with the biological data to make them more usable by users by getting some users on board, what are their needs and how we can address that. So that work is ongoing. Hopefully next year we'll have some more details of that work. These OSTEM metrics are available in the NetCDF format. So all these observation things available in one NetCDF file, GDS compliant file. And then it is displayed in IMOS Live, so people don't have to actually get the data. They can just play with the display tools and get whatever the information needed. And if they need the data, that is also available if they want to do their own analysis. Categorical and probabilistic marine heat wave forecast based on SST ensemble mean from access S2 available for up to 6 months ahead. And we are using all that information together for event-based sampling. So that's from me. Thank you.
Thank you, Pallavi. No, you were perfectly on time. That was, but we'll take questions after the 3 talks. So you sit down for now. Thank you. The second talk, 12 minutes for Rosa. And you're on marine heat waves from space. So I think this is a readout from a big meeting that was held in the autumn.
Okay, so my presentation is to provide you insight of the outcome of this workshop that we did on marine heat waves from space, from detection prediction, that is part of the project CHRSST funded by ESA. First of all, I want to spend a couple of minutes to explain what is CHRSST project and why we organize this workshop. The CHRSST project is one of the projects of ESA on ocean health and aimed to improve the marine heat wave detection, to build up a global atlas of marine heat wave for the last four decades, build up for the product of marine heat waves, and advance in physical process, understanding of physical process involved on marine development and their impact on the ecosystem and services. Since the project started in 2022, we already have several outcomes of this project, and the idea of the workshop was based on this outcome. So during the project, we tried to improve the methodology for detection. We developed the atlas, the 2D and 4D atlas, checking also the impact of different methodology on of detection, and studied and how this use this data to study surface and depth resolved marine wave, and try to observe direct penetration mechanism, and perhaps Salvatore will show you something in the next presentation tomorrow, and improve the understanding and identify also method of data gaps, advance or monitor attribution. So at the end of this project, we prepare a roadmap on future development of the activities, and having this roadmap, we decide to try to understand if our outcome are consistent with the other project outcome. And for this reason, we decide to have a community discussion to make the point on scientific advancement of marine wave, identify scientific observational gaps in terms of observation, prediction, and their impact on the ocean health. So we organized this workshop. The workshop was thought to be in presence in order to have no workshop with presentation, but a workshop with discussion on this part. And the workshop take place in Esrin in ESA, between the 13th and 16th October 2025, with the participation of several, a limited number of experts. And at the end, the last few days, we decided also to try to open the participation online for person that at the last moment was not able to come, like Chris, for example. So the idea of the workshop was aim to two major aims. One, to develop a community white paper on that outline the future research needs concerning the Earth observation outtake for marine heatwave detection, monitoring, and prediction. And second, to define a subsidiary ocean activity that can be developed in the framework of ESA new science strategy that has one of the main activity on extreme hazard, and in the framework of the flagship action between the European Commission and ESA. So the work was then organized, the discussion in different, looking to 4 different objectives. One, what we should do to improve marine detection approach. What we should do to advance marine wave observability, what we should do to advance marine wave prediction, and last one was improving marine impact assessment activity. Here you have the list of this objective. And why we decide this objective? Because before the project, the workshop, we try to send to the list of participants that was decided, taking into account the project in place at ESA, the project in place at the European Commission, and expertise worldwide. We try to propose a possible question to the participant, and this question was used to build up a questionnaire that was analyzed in order to define seed question that was used for the discussion. And the project was, the workshop was organized with keynote talks, breakout session based on these questions, and planning section to make the report and define the recommendation. This allowed us to build up the strategy, to build up a white paper. The white paper aims, after a lot of discussion we had, was that the paper should provide not a current state knowledge, key challenges, opportunity, and recommendation. And this is based also on the fact that we know that marine heatwave is occurring frequently. We know that there is a possible interconnection on climate modes, no long-term trends, and forcing of marine waves, atmospheric forcing of marine waves, and this has an impact. And here there is a plot of the more recent literature paper published on marine heat wave, and if you can see, we have a huge number of papers produced in the recent years, and most of them are related on impact. In the next few minutes, I would like to show you what are the results of this discussion, because the paper is at the third version, and we hope to submit before the summer break. In order to know what come out from this discussion. Each section of the objective is divided in two parts. One, first, state of art, obviously, but the most important part are gaps in knowledge and challenges and opportunities and recommendation. So for the improving marine detection approach, we think that the major challenge is the definition of anomaly in the context of a stationary system. The K parameter is reference period baseline used to compute the climatology, and we show in the paper, and there is written also in several articles published, that this is produce different results. And we know that there is a combination of atmospheric forces, ocean and ocean conditions, often modulated by large-scale climate modes. And we have a huge problem at the high latitude and coastal region that are more challenging environment. The detection of the other important point is the detection of the marine wave at subsurface. To identify the fact that will be different, the climatology will be different, to separate anomalies related to dynamics respect to the anomaly related to the penetration of marine wave towards the vertical. So the opportunity recommendation, this part was, first of all, for the satellite component to use a recent baseline climatology to avoid the more uncertain early satellite era data set, to apply marine heat wave detection to multiple SST data set accounting the level 4 uncertainty. Provision of both the trend and not the trend result can help interpreting the effect of warming background, and developing new methods of marine detection, leveraging advanced statistical method of non-stationary tails is mandatory important point to work on. And the final point is moving from Lagrangian to Lagrangian framework to better follow marine heat wave evolution.
2 minutes, Leo.
2 minutes. I will try to do my best. For the predictability, the major point is that there is a really problem, main gaps of marine forecast prediction capability to capture a stream. It's very difficult that they will be able to catch this part, and this depends really also on the understanding physical drive of marine wave. The remains high complex to interline process occurring on the ocean, and there is lack of standardization how to assess the marine heat wave drivers. So the opportunity recommendation is to leverage marine artificial intelligence models, provide alternative to the traditional dynamical models, to improve the use of new mission SST, to finer tuning data-driven forecast, and adaptation data-driven method understanding the drivers. So the last point is the impact. No, the last point is observation, really. Here there is an additional issue because there is the problem is the ability to understand, understand the impact of marine wave on biodiversity is limited by observation and appropriate spatial temporal scale. And also the challenge is the limited mechanism of understanding between the thermal exposure and the biological response. So here we think that the new mission, satellite mission of Ocean Color for providing hyperspectral can provide more insight. We need for sure laboratory experiment to understand ecosystem response and integrating this data in data. And finally, the part is the observability. And here I think the observation is important to highlight is multiple elements managed by different nations and international entities. This observation system should be maintained at long term, and the ability to timely detect SST stream rely on satellite observation but require continuous improvement to address the user need, especially if we want to have also information driver and impacts. So the opportunity of new mission is relevant. The key key process to achieve new satellite mission that measure not only temporal but also current ocean color all together and help the use of this data set to provide for the better description, also use artificial intelligence drivers. And obviously there will be a request at the end of the paper to maintain also the in situ observational system that we know that at the present has a big issue. That's.
Thank you very much. And the final presentation for now is Ruben, and it's about data inhomogeneity biases, marine heat wave trends. It's 10 minutes. I'll give you a 2-minute warning.
Okay, thank you. There's lunch break afterwards, so I'll try to be brief, and I will try to add something to the discussion ongoing before. I would like to briefly talk to you about what our group encountered while studying marine heat wave trends, and it has to do with data inhomogeneity. So the first thing, let's start from the beginning. When you're doing this type of studies, you may consider climate reanalysis. And what is the main goal of a climate reanalysis? Well, I'm guessing some of you may be tired at this point, so here's ChatGPT response. The main goal is to provide the best estimate of the historical state of the ocean by combining observations with the model. So there is a model, there is some assimilation of observations, and that's actually, well, that's complicating things. And we will see, I will try to explain some of the complications that reanalysis may face first. One of them is the expanding observation network. We all know that the density of data has been increasing, and this is generating an increase in the standard deviation, because where there once was one measurement, for example, and this means there was no standard deviation, now there are a lot of observations with add to the standard deviation. And when your standard deviation of the standard deviation of your data set is changing over time, the analysis of the climate trends, it complicates. But I'm aware this has already been somehow discussed in the community. One thing that may have been overlooked, though, is the assimilation inhomogeneity. What happens when you change your assimilation observational products is something we will be discussing here today in the marine heatwave trend context. So, first of all, what is the methodology we will be using to compute the trends of our marine heat waves? We are interested in the internal variability of our system, so we will trend our data. And just to explain, we find out that the trends in the winter days, because the data we used is daily, the trend in the winter days was different from the trend in the summer days. So we performed a day of year detrending. So this is accounted for. Afterwards, the datasets we will be using are two observational datasets, the CCI version 3 and the optimal interpolation. And the analysis we will be looking at is ERA 5. The period is 1982 and 2024, and the selected region will be the Mediterranean Sea. So with all these ingredients, what results do we get for the marine heat wave trends? Let me explain what is being displayed here. The maximum intensity and the mean intensity parameters of the marine heat waves and its trends. The ones that are highlighted in black are the statistically significant ones, and the others that are in a light gray line, they are the not statistical trends. So these results are not very conclusive. Every dataset is telling a different story. But if we pay close attention to the slope values, actually CCI and optimal interpolation are in closer agreement than ERA 5, which seems to have quite a bit different numbers. So why is this happening? Well, instead of asking ChatGPT this time, maybe we can go to ERA 5 documentation. And the thing is that the assimilation of the observational datasets changed from September 2007 from HATA-SST product, which, if I'm aware, it's a product assimilation every 5 days, to the OSTIA product, which is a daily observational dataset. Also, the grid resolution is different, so we are changing here the assimilation from two datasets that are spatially and temporally different. And what is generating this to our dataset? Is there a possible way to see this? Well, we performed a wavelet analysis, and for those of you that are maybe not aware with this type of analysis, what we're doing here is breaking down the data into different frequency components. The vertical axis is actually the difference period. Since this is a daily data, it starts from 2 onwards. And well, the colors you're seeing here is the intensity of each of the frequency components. But the interesting thing here is the black contour lines. They are indicating the areas where the power is statistically significant compared to the background noise. And I added this vertical white line where the assimilation in homogeneity change. But I think it's not even necessary. You can see the areas from the higher frequency components are now, when OSTIA is assimilated, are now statistically significant. And what is saying this to us is that the structure of the dataset has changed. There is a more simple way to watch this, which is to compute the difference between the SST of one day with the SST of the day before. And this is a spatial mean for the Mediterranean region. We can see this abruptly jump in the daily variability. This time I did not put the vertical line. I guess it's not necessary. So we were thinking, okay, is this the problem? Is this what's making ERA 5 trends looking a bit different? What can we do to solve this? So we homogenized our data from the OSTIA simulation period onwards. We did a moving window, a 5-day window, to match the HATA-SST simulation period daily variability. And what we got, if we computed again our marine heat waves, is this. I will leave you to do the conclusions. You can make your own conclusions. Now the numbers are in closer agreement for the three datasets. However, there is, I think this is something that the GRIS community may be aware, but there is a lot of people outside this community that are not aware of these things. and the importance of these things to the results. So what do we tell them? Just wait for year 6 to solve this problem? Do we give them homogeneous reanalysis so they can play with them and still do whatever they want? As I said, I want to give to you the conclusions, but I think we as a community should maintain to put our efforts to tell the users and keep the producers making products that are homogeneous and account for these problems, and also to make the outside community aware of the importance of these problems in their analysis. Thank you very much.
Okay, thank you very much. Very, very interesting and makes a clear point. We are a little bit late, but I think we should have a time for at least 5 minutes for questions immediately to those 3 talks. So we had the Pallavi's overview of the Australian work, and we had the report on the meeting that was held last autumn from Leah, and this interesting talk by Ruben last. So any questions on any of those? Jorge, you can go first. Any other?
Just a quick question on the issue of data gaps. Are the data gaps driven primarily by cloud issues? Are there other issues, driving gaps in the data?
Is that addressed? Who's that addressed to, Jorge?
Yeah, the first talk. I'm sorry.
Pallavi, yeah.
So, yes.
Well, that was a simple answer. Yeah.
No, no, I was just checking whether this thing is working or not. So yes, those gaps are in the infrared channels, and those are primarily with the clouds. Yes.
Any more questions?
We have one online.
Right. Well, the questioner
Hello.
You can speak.
Yes, hello. Can you hear me?
Helen, hello.
Yes, hi, how are you? My question is for Pallavi. Great talk, wonderful. And oops, not screen share, sorry. My question was about adding AMSA2 SST to the geopolar L3S composite, which is a great idea, a great thing to test. Have you had time to validate it yet against independent in situ data? And what did you find? Did you find that it made it less accurate or more accurate, or didn't make much difference to accuracy? Thank you.
So, is that geopolar multi-sensor product you are talking about? So that's the
Yes, you had a plot
Yeah.
adding AMSA2 to reduce to reduce the gaps.
Okay. No, that is very initial work. We didn't get time to validate it against in situ yet. But then the addition of Himawari 8, so geopolar multi-sensor, that we have checked with the validation, and we found similar statistics that we were getting with the multi-sensor that was made only with the polar orbiters. But addition of AMSA3, yes, we still have to validate it.
Yeah, that'll be interesting. Thank you, because AMSA2 is generally less accurate compared to in situ data than, say, VIIRS or
Yeah. So that's
Himawari
why
8.
we are planning to keep it separate. We won't mix it directly with the infrared channels. And we
Okay.
will notify that with the quality levels and
Oh. Okay, great. Good luck.
Okay.
Thank you.
Thank you. Any questions for Leah or Ruben at this point? Yep, there's one from Veronica. Oh, and I saw Veronica first, so we'll go Veronica, then Ed, and then that will be the end of the questions.
Leah, I saw on one slide you used a phrase called cold spells, and I think that's interesting that then you didn't talk about it much after that. So it's fine that we go put all this effort into statistically defining a marine heat wave, but the biology, isn't really following. I haven't seen any evidence that the biology is following our strict concerns about how we document. I think it's good that we do, and there's a metric to chart changes, but the cold spells I think would also be important for the biology side, and if we're targeting potential biology users, that's
Yes, yes. In the KERIT project, we built up the atlas for the last 4 decades, which include both marine heat wave and cold spell, and obviously discussing the future. We thought that will be very important because obviously the organism. When we will look to the impact part, the organisms are sensible to the extreme, independence, high value of the extreme or low value of the extreme. And another part was not easy to show in a few 12 months all the discussion we had during the workshop and in the preparation of the paper. One of the things that we thought, and we started with KERIT, but will be very important to provide to the user that wants to use the impact the absolute value of temperature, because obviously it's not only the anomaly that produce impact on the organism. Obviously, an abrupt change has impact, but also the absolute value of reached is an impact. And the outcome of the discussion was to have both the trended and not the trended temperature, because it's obviously the adaptation of the organism can act in a different way respect to an abrupt change. So there is
Thank you.
Thing.
We have just one brief question from Ed, and then we'll wrap up. Thank you.
Yeah, I just have another brief questions for you, Rosa. I saw that one bullet where you had like machine learning approaches for ocean circulation. Maybe say a few words about why that is better. Is it faster than just using a ocean model that's already running, or what's going on there?
Yeah, the model community trying to do a combination of the two approach. So working on the artificial intelligence to reconstruct some high variable pattern of the events. There is, I am not the modelers inside, but the team that was involved in the discussion that are working on modeling component, they identify the two things. Okay, there is a lot of discussion, especially in Europe, related to the digital ocean activity that the artificial intelligence can substitute the use of the equation. But this is not the real solution. The real solution is the combination of the two approach. And I think that will be very important to, in the future, to have research to make this type of intercomparison and use of the.
Okay, thanks.
That ends the session. Thank you very much. Enjoy your lunch, and let's thank the speakers once again.
Ten minutes? 40, 10.
And like that, yeah, I think it's
Five.
yeah.
5. Then
the questions and discussion on GRIS priorities. So we're going to be starting at 10 past with a presentation from Marisol. Can we check that you're there, Marisol?
Yes, I'm online.
Perfect, perfect. We can hear you nicely. That's great. Well, I think we're all gathered in the room, so I'll give you the floor. Please go ahead. I'll give you a 2-minute warning for your 12-minute talk.
Sorry, I think you're going to present my slides with audio.
Yes, we can. Oh, I see. Right. Yes, we're playing this one, are we? Okay.
Yes, otherwise it cuts off a lot.
Fine.
Okay.
So we're seeing on the screen and it's playing.
We are from SIST in Baja California, Mexico. Our work is entitled Sensitivity of Marine Heatwave Metrics to SST Product Choice in Gradient-Dominated Coastal Regions. Marine heatwaves are extreme events defined as periods of 5 or more days with SST above a threshold given by the 90th percentile of SST anomalies at a given point. And these extreme events have strong and important effects on the marine ecosystems, and I don't think I have to tell you more about how important these events are in our planet. In this group, we know the importance of sensitivity to chosen SST products for different metrics. And we are not the only ones that care about this. Here, there is a paper on sensitivity of marine heatwave metrics, particularly in the tropical Pacific. And they found that although year-to-year variability is similar across products, there are important differences in the metrics across every single of the product. I recommend this paper. It's very thorough on describing the sensitivity. Here we are interested in the coastal areas, especially those with strong temperature gradients, because these gradients are associated to processes often relevant for the ecosystem. And therefore, the marine heatwaves in these areas have large impact on the ecosystems and the communities that depend on. For this analysis, we selected several coastal regions across Mexico and the Caribbean. But in this talk, I'll focus just on the peninsula of Yucatan as an example of the type of differences we encounter across SST products. And rather than overwhelm you with comparison across metrics and products, I will talk about the differences between two products. First, the medium resolution optimal interpolation SST, which for many years has been the product of choice to study marine heatwaves. Second, the Copernicus high resolution CCI SST product. Here, I'm showing you maps of long-term average of SST for these two regions. Other than the differences, at the coast due to the resolution in the area of cold SST north of the peninsula, but products are very similar, as you can see. This region is characterized by strong vertical SST gradients in the northeast of the peninsula, which is related to upwelling of deep waters from the south, and where the main differences exist. Not unexpectedly, there are important differences in the marine heatwave metrics between these products. One basic metric is the intensity of the marine heatwaves, defined as the mean magnitude of the sea surface temperature anomaly during the event. This metric shows important differences in magnitude between products, although similar in spatial distribution. Similar differences exist in other products and in other regions, although I'm not showing them here. However, for these regions and these products, the metrics of duration of the marine heatwave show stronger similarities in magnitude distribution, except for the northeast corner of the peninsula, where the strongest SST gradients occur due to upwelling. Again, for other regions and products, comparisons differ. But our goal here is to show you that differences are not uniform across the region and could be important on the areas of interest. And here another metric. The percentage of area classified as marine heatwave over a year. This time we are showing three different SST products. The optimal interpolation SST is in blue, the CCI SST is in green, and OSIA in orange, which is closely related to CCI, but as you can see here, they already show differences in this metric. Internal variability across products is similar, and in all cases, they show an increase in marine heat waves in measured years. However, there are years with important differences among the products, like the 1982 and 1983 El Niño, and especially around 2014 and 2016, when this region experienced an extreme marine heat wave. Some of these results are unexpected. However, here we wanted to dig a little bit deeper, because in the last couple of years, there has been a debate over the definition of the baseline used in the diagnosis of the marine heat waves. The basic definition of marine heat wave uses SST anomalies with respect to a baseline period of climatology, usually a period of 30 years. And then over those anomalies, we calculate a 90th percentile threshold that defines the marine heat wave. With time and the upward trend of global SST, this definition is not as simple anymore. With a fixed baseline period, the frequency and magnitude of the marine heat wave increases annually, and it will reach a point in time when we are in a permanent state of marine heat wave. Therefore, some researchers propose that we detrend the SST data before calculating the marine heat waves, to ensure that we are only looking at extreme SST events. Furthermore, other authors suggest that we take shifting baselines to ensure that we are only considering the 10% of extreme events at any point in time. All are good suggestions and are in use already for different applications. But the important point here is that they all lead to a difference in marine heat wave metrics, as you can see here. I recommend this paper, Smith et al., for a more in-detailed discussion about this. Here, we want to look closer to the second option, the one that trending the SST data before diagnosing the marine heat waves. Let me show you the linear trends of SST for both products. Both plots are in the same scale of change in degrees per decade. We can see that there are important differences at the coast, of course, and at the northeast point of the peninsula. But we can also see differences in magnitude away from the coast. One important point here is that these trends are not uniform across the regions, and these spatial differences exist across all SST products regardless of the resolution. The general idea here is that if we remove SST trend, only the extreme events of SST will remain, and maybe the metrics might be more similar among products. On the Yucatan Peninsula, this is true for the mean intensity metrics that become similar between SST products. However, for the duration, it introduces differences that didn't exist in the non-detrended calculation. For other regions and other products, there is not a single result in which ones are more similar or less similar once detrended. Percentage of area in marine heat wave state metric, we can see in the plot below that the trend in the SST data introduces more pronounced differences among the SST products, and that these differences are not consistent through time. This is likely due to the heterogeneity of the SST trends in these regions with strong gradient. Here are the trends of SST on the optimal interpolation SST product, which is the one that barely shows this coastal gradient, and even here we can see that the spatial distribution of the trends are not homogeneous. In summary, the marine heat waves are highly sensitive to the choice of SST product, which is of no surprise at all, especially in areas of strong temperature gradients. However, it is not just about the resolution or the choice of product. One factor that seems to be important is the long-term trend in SST in each product and their spatial distribution, as they are not linear and they differ greatly among products. Finally, it also prompts the question if it's advisable or adequate to use an ensemble of SST products to diagnose marine heat waves, as we do for other types of metrics involving SST. Thank you for listening.
Thank you, Marisol. I hope you can stay online, and we'll be taking questions after the three talks. The next speaker is William Skirving.
So, seeing as there was going to be a marine heatwave session at GHRSST this year, I thought it might be interesting to some of you to hear about the history of what is possibly the oldest global marine heat wave, well, operational marine heat wave. It was operational I was stuck on. Product suite in the world, which is the Coral Reef Watch products. And because some of you don't necessarily know my history much, I'm not working with Coral Reef Watch at the moment, but I'll explain how I fit into the equation as we go along. So the product suite as it stands at the moment, this is the core products, the operational ones. SST, SST-A or sea surface temperature anomaly. That's a daily anomaly, by the way. This is a hotspot, which is an anomaly that is derived to explain the daily heat stress of a coral. This is a DHW, degree heating week. It wasn't named by a physicist, by the way. That is an accumulation of hotspots, so it's an accumulation of the heat stress. And the categorization of the DHW was called bleaching alert areas. I was actually somewhat against the development of the categorization, but turns out to be Coral Reef Watch's most popular product. So when Alastair Hobday in 2018 came up with the notion of categorizing a sea surface temperature anomaly to create marine heat waves, I produced this product just for the fun of it. Hardly anyone uses it, I might add. So back in the beginning, all started with Al Strong, who used to work for NOAA, who was seconded to the Naval Academy, and he was teaching remote sensing to the Naval Academy students. And then in 1989, along came bleaching in the Caribbean, which opened people's eyes to this phenomenon and started people worrying about it. And some of his students became really interested to know whether or not you could use satellites to track coral bleaching, because at that stage, Peter Glynn had already written a paper that described coral stress as being 1 degree above the summertime expected maximum. So one student in particular, midshipman Michael Gleason, got very interested in it. Clearly he was a smart kid, ended up being a Navy SEAL, by the way. He invented the product, well, the algorithms that became the products for hotspot and DHW. So not a NOAA product, as it turns out. Oh, sorry, I think I should go backwards. Maybe not. Yes, I think I do. So Al was then moved back to, when they saw that that in 1998, Al used the hotspot to predict the, not the DHW I might add, which is interesting. He didn't know how to interpret it at that stage, but he used the hotspot to predict the bleaching on the Great Barrier Reef. And that had headlines all over the world. So NOAA recalled Al, and then they formed Coral Reef Watch in 2000. I was involved with Coral Reef Watch from almost the beginning of it, from 1998 onwards, pretty much, is when I first met Al, because I was working at the Australian Institute of Marine Science at that stage. And I ended up being seconded to work with Coral Reef Watch in February 2002. So the original product was based on the NOAA 50-kilometre twice weekly MUT. Remind me again, Andy? Main Unit Task. What an acronym. Anyway, so it was twice weekly, 50 kilometres. There's more detail in that. If you're curious, just ask, but I won't go into it here. The MMM, which is the monthly mean maximum climatology, which was the definition of a summertime expected maximum. was derived using an AVHR data set that University of Miami had, 36 kilometre resolution, and that was 1985 through to 1990 and 1993. 91 and 92 was skipped because of the aerosol due to Mount Pinatubo. Hotspots were defined as sea surface temperature minus the MMM. Notice the MMM is a static climatology because the corals have adapted to or evolved to cope with a static temperature above which they freak out, below which they're very happy. The +1 comes into it where it was decided that +1 above MMM, in other words, a hotspot of 1, was stressful. So DHWs were the accumulation of hotspots with that were 1 or more over a 12-week period. That 50 kilometre product is this. This is SSTs, SSTA, hotspots, DHWs. Okay, so then moving on, we improved it over 2003 to 2008. The products also became increasingly popular. By about 2008, it was an absolutely indispensable product for most coral reef managers. We invented the idea of virtual stations so that you could do time series analysis on a single pixel, and they're very popular. This is the time that the satellite bleaching alerts were introduced, so a categorization of the DHW product, and they become ridiculously popular. We also improved the coastal resolutions by shrinking the land masks and allowing the 50 kilometre pixels to bleed into near the coast, and then overlaying a higher resolution map on top of it, and it worked really, really well. And the climatology was improved because the AVHR Pathfinder data became available, so we moved from 1985 to 1993 climatology, and obviously this was done in 2007 probably because we had 1985 to 2006 data. So then Andy's blended product was being developed between 2009 and 2014. It briefly went through a period where it was 11 kilometre resolution, but quickly settled on being 5 kilometre resolution. I can't remember why, but we'll worry about that later. But 5 kilometres was a good size. It meshed in with a lot of other things that we were doing at the time. We were still using the 4 kilometre AVHR Pathfinder data for the climatology, but we were then able to move, obviously in 2013, to extend the climatology from 1985 to 2012. That was an arbitrary choice, I might add, because the data was there, not because we had a physiological reason from a biological point of view. And we also extended the climatology of the 50 kilometre product at that stage. So we still didn't have the 5 kilometre product as a operational at this stage. Then the 5 kilometre product was operational for a while, and I was very frustrated with the fact that we were creating anomalies using apples and pears. In other words, the data that was being used for the climatology was a very different data set to the data that we were using for the near real-time data. So I decided that we needed to come up with a better product, and that was when we invented Coral Temp, and discussions with Jonathan was what gave me the idea of that it was possible, and Andy pretty well made it possible. So what we did was we used the original Ostia reanalysis, which is the version 1, which is no longer available easily. So that stretched up to 2002. Andy and his team, I should say, kindly reprocessed the blended product way back to 2002 using the Ostia reanalysis as the bias correction, and then at the beginning of 2008, it switched over to using the Ostia near real time, and that is how the product still runs today, is it not, Andy? So it's just run as a near real time product and bias corrected against Ostia near real time. So that gives us the final product. We get to the first slide that I had. So the evolution of the MMM climatology. So it's the climatology that drives all this. You change climatology just a little bit and the DHWs change a lot. So very sensitive to the climatology. So the climatology from 1994 to 2007 were designed for the MUT, were based off the I've got approximately 19 kilometres. That's 36 kilometres. University of Miami data, and that was the original 7 years. Then in 2007, we had the ability to switch over to Pathfinder data. So we derived a 50 kilometre product out of, or climatology out of the 4 kilometre Pathfinder, and that went from 85 to 2006. Then 2013 to 14, we increased that climatology for the 50 kilometre product to 2012. Then in 2014 to 2018, we started using the 5 kilometre blended product and generated a climatology out of Pathfinder, but we're still at this stage using apples and pears for our climate for our anomalies. So we switched over to Coral Temp in 2018, and therefore we were able to create the climatology from exactly the same data set that we were using for the near real time product, and that is how it is to this day. So last slide, Chris. I don't know whether you've been waving at me. I haven't been looking. Future of DHWs. This is my opinion because I no longer work for Coral Reef Watch. I'm a foreign national, and Trump didn't like foreign nationals, so I lost my contract. So problems with the use of the Coral Temp product. It is not a perfect product, far from it. It has a cool bias from about, and this is about, I'm arm waving here, from 2005 backwards. And that's literally because the algorithms were using drifting buoys to and a regression-based algorithm. So the further back you went, the higher the worse the bias got, basically. So the problem with this is you can't compare DHWs of today with DHWs before 2005. So they're useful. Pre-2005 DHWs are useful for spatial understanding where was the stress more than somewhere else. But you can't compare, say, 1998 bleaching with a 2016 bleaching, for instance. They are fundamentally different products, and yet people do it all the time. It is only not based on nighttime data, so there's no diurnal variation, no ability to come up with diurnal variation at this stage. And if you did have an ability, and this sort of goes to a question that Veronica asked me a little while ago, you'd need to be able to come up with a climatology. So how we run the diurnal variation story way back in time, I don't know. So that's important because we now know that resilience is resilient corals can be found using diurnal variation maps. DHW is also only designed to monitor the onset of bleaching. That's not mortality. They use it for mortality, but it's a weak correlation. So how do you improve it? Well, obviously you move to a modern level 4 SST product, and CCI is a darn good example of that. you'd have to improve the climatology, preferably pre-1980. Whether or not we can do that's another story, and I'm not suggesting we do it with satellites. We didn't have satellites, but it might be possible using a version of HADST. Now that they're tuning it to CCI, it might be worth having a look at that. And of course, all of this work will require a complete rework of the DHW algorithm. And this is simply because if you apply DHWs to a largely biased consistent data set like CCI, you will find that the algorithm will just blow up and it won't work. So it's very sensitive to the data set that it uses. If you don't use Coral Temp, you won't get the right answers. It's that simple. Thank you.
Thank you. And the final talk before we have the question and answers is from Ko Chuchida. Please take the floor. It's 10 minutes. I'll give you a 2-minute warning.
Good afternoon, everyone. I'm Ko Tsuchida from the University of Tokyo. Actually, recently moved to another research institute, National Institute for Environmental Studies, Japan. Sorry, my talk is not directly about the SST product itself or the marine heat waves, but about like anomalously high SST and its impact on global mean temperature and global climate. So the global mean surface temperature reached exceptionally high levels after 2022, especially in 2024. The global mean surface temperature even exceeded 1.5 degrees Celsius above the pre-industrial levels. So we want to know the cause of this recent record high global mean surface temperature. And yeah, there are some studies suggesting the importance of ENSO, like the transition to El Nino caused kind of abrupt jump of global mean surface temperature from after 2022. But there is also another research suggesting that ENSO or tropical Pacific variability alone cannot fully capture this abrupt increase of global mean surface temperature. Ooh. So therefore, we focus on the North Atlantic. The right figure shows that our time evolution of North Atlantic annual mean SST anomalies, and you can see the anomalously high SSTs for 2023 to 24 for 2 consecutive years associated with the basin-wide marine heat wave. So we want to investigate this anomalously high SSTs and its impact on global mean surface temperature. So today we don't talk a lot about this mechanism about the marine heat wave, but its impact on global mean surface temperature. So to address this point, we conducted a set of climate model simulations, usually known as pacemaker experiments. So in the pacemaker experiments, the SST anomalies are restored to the observed anomalies. And yeah, through this method, we can isolate and quantify the influence of SST variability on a specific ocean to the global climate. So in our experiment, we conducted 3 sets of pacemaker experiments: the tropical Pacific pacemaker experiment, North Atlantic pacemaker experiment, and tropical Pacific plus North Atlantic pacemaker experiments. So in each pacemaker experiments, the SST anomalies in the colored region are restored to the daily OI-SST anomalies. And in our analysis, we mainly compare the anomalies relative to the 1991 to 2020 climatology. Oh, it's not so clear. Sorry. So here we show the results. So this is the time evolution of annual mean global mean surface temperature anomaly for each data set. And you can see that the tropical Pacific pacemaker, denoted by red line, well reproduces the observed global mean surface temperature over the past few decades, as indicated in previous researches. But it cannot for 2023 to 25. But by incorporating the North Atlantic influence, I mean the anomalously high North Atlantic SST influence, represented by TP plus NA pacemaker experiment, its ensemble mean remarkably captures the observed global mean surface temperature anomalies. So here we also show the spatial pattern of surface temperature. Here we only focus on the internally driven components. So the external, the forced component is subtracted. So as expected, the surface temperature anomalies in the restored region, like the tropical Pacific or North Atlantic, are consistent between the observations and each pacemaker experiment. But the point here is that the surface temperature increase over the land regions, especially over the Eurasian continent, is reasonably captured when the North Atlantic warming influence is included. So this feature is especially clear when we compare TP tropical Pacific pacemaker and North Atlantic pacemaker. So you cannot see kind of clear warming signal in the tropical Pacific pacemaker, but a substantial warming over the Eurasian continent in the North Atlantic pacemaker experiment. So this indicates that the North Atlantic warming can play a key role in inducing surface temperature increase over the Eurasian continent. So here we also demonstrate the importance of northern mid-latitudes to the global mean surface temperature increase. So we kind of decompose the contributions to GHRSST anomalies into different latitudinal bands. I mean the tropics, northern extratropics, and southern extratropics. So this is the case for 2023. And in this year, associated with the El Nino onset, the warming over the tropical Pacific is mainly manifested over the tropical region. And when the North Atlantic warming influence is additionally included, larger warming appears over the northern extratropics, actually larger than the tropics. And so we focus on the northern extratropics, and then we also further decompose the northern extratropical contribution into North Atlantic influence, North Pacific influence, Eurasia, and residual influence. So, owing to its larger area extent, the Eurasian contribution is actually greater than the direct contribution from the oceans. And when we focus on the internally driven component, you can see that the Eurasian warming is not reproduced by the tropical Pacific influence. And another important point is that part of the North Pacific warming is also reproduced when the North Atlantic warming influence is included. So the physical mechanism needs to be clarified as a future topic, but we expect the anomalous warm advection by the mean westerly winds can play a key role since we find a clear warming over the downstream region of the North Atlantic. And
2 minutes.
Yeah, thank you. this is the case for 2024, but we find a kind of similar feature as indicated in 2023. And so finally, we try to investigate the potential impact of North Atlantic SST variability on future global warming surface temperature increase. So to achieve this goal, we construct a simple regression model. And so here we only focus on the answer independent component. So we calculated regression coefficient of global warming surface temperature against North Atlantic SST based on the intermember anomalies in tropical Pacific pacemaker experiment. And this is the calculated regression value in the associated surface temperature pattern, which also shows the warming over the Eurasian continent. And by using this regression coefficient and by multiplying the North Atlantic SST deviation from the SSB CMIP6 SST scenarios, we reconstructed GSAT, which is shown by blue bars, which actually reasonably captures the GSAT global warming surface temperature anomalies represented by North Atlantic pacemaker. So to address for the future component, we hypothesized two scenarios about the North Atlantic SST time series. So scenario one is that the North Atlantic SST remains neutral after 2025, which means just simply follows SSB scenario. And scenario two is that we have another warming event in the coming few years. And then right figure shows the reconstructed global warming surface temperature. And in case of scenario one, the global warming surface temperature decreases below 1.5 degrees Celsius and just simply follows the scenario projected level. And in this case, the timing at which 10-year mean global warming surface temperature reaches 1.5 degrees level doesn't change substantially. In contrast, in scenario two, global warming surface temperature rises substantially again, even surpassing 1.5 degrees Celsius, even without the anson, I mean the tropical Pacific influence. And in this case, the timing at which 10-year mean global warming surface temperature reaches this level can be advanced a little bit, I mean a few years. So, and this is the final slide. And yeah, I want to just emphasize that in addition to the tropical Pacific influence, the North Atlantic SST variability, especially exceptionally high SST, can influence on global mean climate, especially global mean temperature. So the further understanding of marine heat waves and especially the improved prediction of North Atlantic SST can also play a key role in global climate prediction. Yeah, that's all. Thank you for your attention.
Thank you. Very good. Very interesting talks, all of them. So we have questions for the three speakers, Marisol, William, and Cole. Any questions? Shakila.
Hello, enjoyed the talks. William, you know I'm going to ask you a question. I'm with NOAA and work with the Coral Reef Watch team and know that all the work you've done over the years with the team in general. So one of the questions I have for you is, as you talked about the trying to use a different SST and you're getting the products are blowing up, is that sort of an algorithm problem per se, or what is actually going on there?
I think the main thing is the climatologies are hugely different. And because there's a cool bias in coral temp, the climatology is naturally cooler. So if you've got a sea surface temperature like CCI, that is less bias, well, the bias is consistent. It doesn't matter what the bias is as long as it's consistent. Then the climatology is going to be warmer. And therefore, the hotspots will be fewer and the DHWs will be less. So it literally blows up. So you get a situation where corals start bleaching before you even get a DHW recorded. So it's hard.
Bias, and I'm trying to understand. Okay, and that doesn't resolve? Oh, I'm sorry.
We've tried to mimic the biases in coral temp, all of these sorts of things, but nothing seems to work. It is literally tied to the coral temp product, which is flawed. So to move forward, the DHW needs to be completely reworked. It needs a new algorithm. And for that to happen, you need to fully understand why all those terms are in there. None of the terms are there for a bad reason. So it's going to be an interesting, process. I hope to get around to doing it.
Okay, good. Any further questions? Yeah, Niraj, yeah.
It's a general question for the marine heatwave community as to what scales these phenomena should be observed. Like people say that very high resolution SST is required. But these phenomena are happening at a larger scale or a smaller scale. So that is not really known. Can you please throw some light on that?
Depends on why you want the marine heat wave in the first place. Marine heat waves, there should be a million of them out there because there's a million reasons to have one. Coral reefs are one reason. In that instance, a high resolution, the higher the better. If you're looking for something like trying to understand PDO, ENSO, those sort of large scale climate variables, then lower resolution would be fine. You'd be more interested in higher radiometric accuracy than spatial resolution. And for that matter, the climatology matters too. And this is the kicker with all of this. You can't have a climatology up if you want to use your the marine heat wave to look at biology. Then you need to have a climatology set for what the biology that you're interested in has evolved to or adapted to. In the case of corals, it's somewhere in 1950, 1960, not in the current day. And because they started bleaching in about 1980, then that means we've already pushed past their thermal threshold. So climatology built post 1980 is wrong for that purpose. So it depends on the purpose. If you're looking at something like coccolithophores, they're a hardy little character, and you might be able to have much more success with a climatology that's more recent, for instance. So it really depends on what you're using for as to the resolution and the length of data set that you need to create it.
So that means the climatology, if we are looking at high resolution features, should be also built on a very high resolution data set.
Oh, the climatology should always be built on the same data set that you're using to create the marine heat wave, if at all possible, and the resolutions should always be matched. So I get back to the resolution depends on your purpose for the marine heat wave in the first place. There's no one algorithm fits all. It's going to be different. For the notion of a marine heat wave should be more flexible than it seems to be. It should be tailored to the purpose for why you are deriving them in the first place.
Thank you.
So the point about the resolution was also made in Marisol's talk. Marisol, I've got a question for you if you're still there.
Yes.
Yeah, great. You mentioned at the end, right at the end, the idea of using ensembles to address this issue, but I wasn't quite clear what you intended to suggest by that comment. Could you explain?
Sure. I'm not sure that I have an answer for that. When I started this analysis, I thought that comparing high resolution, there's going to be some biases that were going to be easy addressed by averaging, maybe taking an ensemble. But then, I mean, and what I meant at that point was just taking the mean of all the metrics, right, among different products. However, once I start considering the baseline and the trend, turns out that now it's not that easy. Now the anomalies are somewhat artificial or very different between products. So at that point, I don't know if a mean value in between is enough, or maybe taking the limits, the higher and the lowest. I'm not completely sure. I think that there were more differences than I wanted to see among products.
Yes, yes. Thank you. Any other
So
questions?
I've got a question for
David.
Bill.
Yeah, go ahead.
Which is, how do you relate to the Hobday definitions? You know, the 5-day thing, you're using a 12-week period to define hotspots. And obviously biology plays into this very strongly, but I'm sort of curious how you're thinking about that difference between the physics from Hobday's definition and yours that's more biological.
Alistair and I have had long conversations about this, and we don't agree. Well, we do in many ways, actually. The 12-week, one of the things that we should do when we reinvent DHWs is to eliminate the 12 weeks. There should be no 12 weeks. It should just go. We chose 12 weeks because at the time that we invented it, a bleaching event was 2 weeks long. It was over and done with in 2 weeks. Whereas now you can get a bleaching event that literally lasts multi-years in one location. The temperatures can be over the MMM for a whole year or more. So it's completely different. In fact, the DHW have topped out a number of times now. So the notion of a length of time, I would suggest, I mean, I talk about how corals don't have calendars, so the notion of a variable daily climatology is nonsense. I also would suggest that the physics of this world doesn't care about a calendar either to a large degree, although it's embedded in the physics, obviously, because of the orbit of the Earth and so on and so forth. But the point here is that I'm not sure why 5 days was even chosen. It seems to be an arbitrary choice. In fact, a lot of Alistair's ideas were largely arbitrary. They were just an idea, and they've just taken off. And I think to a large degree because he chose a great name for the product.
Last invitation for any other questions before we move into the general discussion. I do have a question for Co, actually, on the North Atlantic. You showed the importance of the North Atlantic in the global context quite clearly. I think that was nicely shown. But in that particular year, was it mainly the meteorology that drove that anomaly in the North Atlantic? Was it mainly wind, or was it mainly solar? What combination of meteorology was important?
So sorry, I couldn't hear the last part of your question.
What combination of wind or solar radiation or air temperature or other meteorological drivers was driving the North Atlantic in the hot year?
I think both like the reduced trade winds. I mean the weaker trade winds. Causes shoaling mixed layers. Which causes mostly high SST, and also the low level cloud reduction. Causes enhanced incoming shortwave radiation, which also causes.
I've read some papers that Saharan dust might be important in the south of the North Atlantic, the subtropical North Atlantic. Do you think that's true as well?
So sorry.
Saharan dust, is this a relevant factor?
Sorry, I couldn't hear.
Saharan dust.
Saharan dust.
Yeah.
Yeah, I'm not sure whether the aerosol effect was important for that, but at least if the SST anomaly once increases, it can also act to reduce the low level coverage, so which also act to enhance the incoming radiation. So I'm not sure about the aerosol effect. But it might play a role.
Thank you. Thank you. Great. Well, we have some time to think about GHRSST priorities in the context of this session now. And I think one obvious thing that's going on is the white paper, which Leah presented the structure of, and which many people were involved in so far. I guess this is in progress, and you didn't exactly invite everybody to contribute at this stage, because I think it's quite well advanced by now. But what's the plan for the white paper from now on, just briefly?
We have the third version of the paper written and sent to the co-author to a review. And I think the crucial point of this review, apart the format, will be to look at the last section, that are the conclusions part, in which we summarize all the recommendations of the different objectives. Perhaps some of the outcome of this discussion can be included, no, perhaps, I'm sure.
Yeah.
I suggest that some of the recommendations that coming from this discussion can include it in the summary paper part, because I think this paper, if it's accepted to review, in any case, it's important for the European Commission and for ESA for the future development of research activity. So my idea was to make the workshop to collect all the feedback, because we should, I think, to have to do also today with the summary of the history of my heatwave and the results coming from other presentations. I think we are really in a stage in which we should try to go a step forward on this activity. Also because it's requested by a user that wants to have the impact. So to have an easy understanding of what is the situation, the forecasting of the heat wave, it's very important. So I don't want to promise for, because we have a lot of authors in the paper, but I think if something comes from here, this can be added in the paper, and perhaps also add the other authors, because we are a lot, so it's not a big issue.
Yeah.
If to have an additional couple of authors, I think. Okay.
Okay, so you've got the idea you can influence the paper through this discussion. So get all your ideas together. But we've had the almost expressed the opposite opinion that we should not be making heatwave products in general, but that what matters is specific conditions for specific species. So maybe as a GHRSST community, you could say that our job is to make the SSTs and to talk to users to make sure they understand the data and help them generate their version for the specific question they're asking, with the specific species or in the specific environment that's relevant to them. So throw that one out as that GHRSST shouldn't go any further with marine heat waves, because our job is to help the users make what they need. So that's a provocative statement. Hopefully that'll get some reaction. No, not from William, from someone else. And we know you agree. No.
I think if we want to come with a new general suggestion how to improve the detection, of how to use all the informal data, that this should come from this group.
Yes, I think
so.
That's a good point, that the fact that the products are so discrepant, even if we use the same climatology period, and even if we're just using different products, that is telling us something about the consistency of what we're doing and indicating something about quality. So perhaps that is an angle that we should be thinking about together. I don't know whether the Marine Heat Waves group wants to do some systematic comparisons in that direction. That might be something for the task team to think about.
It's always on us. I don't know how you manage. No, I was wanting to make just taking your last question. I think at the end, well, now it seems that we are converging, that the baseline and the fact that we are in a system that it's not non-stationary, so the mean is changing. We need to take into account that if we want to study the physics and the variability. My point here is that maybe for the point of view from biology, it shouldn't be called a marine heat wave. Maybe it's something like heat stressing. I'm pointing what you were saying. I think it's just a matter of vocabulary, and I think we are not, the objective is not the same. So the procedure is not the same. So if we want to study really the variability of the marine heat wave, for us it's clear that we need to detrend. Otherwise, we are in a marine heat wave, in a permanent marine heat wave. So from a physical point of view, it has no sense. We need to, because you are assuming that your system is stationary and it's not. So I think instead of, I mean, I think for the most of the community now, at least in the physical part, it's clear that we need to detrend. It seems it was not like that a few years ago, and there are many literature, and it's a hot topic, and everyone is working on that. So this is one point, and the other point that you were arising from the biology point, because it's the same for us in my institution. We have biologists, a lot of biologists, and it's that from the point of view of biology, it's clear that the trend matters. The species has to deal with that, and maybe we should begin to think in another term. It's not a marine heat wave in that sense. I don't know.
Obviously, a wave start and then come again. If it starts continuously, it's not a wave in this sense. I think there is a step to understand how to treat a non-stationary system. And this imply a different approach respect to a simple anomaly. But this is really depends if we want try to do something on this that require an effort, I think.
Yep. Go ahead.
Turn it on. Yeah. Hello, everyone. Falcini from CNR. You know, Leah was my boss. And and just to add 5 cents to this conversation, actually, we started to use sea surface temperature, marine heat wave time series, and so on to try to check data with mortality of shell farmers, oysters, mussels, and so on in a Mediterranean Sea. And two problems that are actually touching the discussion we're having now. No absolute correlation. So heat waves, anomalies, it's not the sufficient conditions, sufficient things that you have to observe. You have to observe a several phase state situation. So you had to expand a little bit what you're looking for, and not just to be rigid on SST, but the ocean is complex. Behaviors of energy. I'm a physicist, I'm not a biologist, but I'm touching with my hands now that, they die when they want to die and you don't know why. The other point is, and I think this is the main point I wanted to make, is that in a physics community, satellite oceanography, whatever you want, we deal with a deluge of data. We have degree of freedom to choose the baseline, to choose the data sets, and so on. And when we try to compare all these things with the biological data, there is no match in terms of left and right hand. I have tons of data versus 5, 6, 7 data, really sparse, and so on. So maybe the main take-home message is that if we really have to reinforce the collaboration with marine biology, we need to try to expand the community that and make an effort to have data that they start to talk or not talk to each other, but the not talking has to be in a physical meaning, and not just because I'm comparing giga and gigabytes of data with nothing. Pretty much that's the problem I'm having, and I want to be honest. And it's not complicated, it's complex, but if it's complex, we need to have a huge interaction, because marine heat wave in the Mediterranean Sea, they doesn't correlate, and because we have few points on the other side. Pretty much that's it.
Yeah, interesting. Thank you. Well, I think we have wrapped that discussion up. Thank you very much for all your contributions. We now move.
Just one point from the GPO part.
Yeah.
Last year, we agreed, or it was one of the priorities, to start a task team on marine heat waves. This is something we need to report to the advisory council. It didn't start, so I just bring that to the discussion. I don't know if we are still considering that. If so, if we have volunteers to do that, and that's it.
Yeah, great. So if you still want to see such a task team, let us know. Yeah, thank you. Okay, Daniele.
Yes, thanks a lot for agreeing this last input from my side. So Christina mentioned the task teams, and there is one thing that came into my mind since previously William and Nirag mentioned the issue of resolution. I was wondering if it makes sense. I don't have the answer for that now. That GHRSST provides some guidance on the contribution of future ultra-high resolution missions for marine heat waves monitoring, since baselines at very high resolutions are not easy to access. So if it's possible to have some guidance on that side, and if this could potentially be addressed to the coastal high resolution task team. Thanks.
Okay, so hopefully that's been noted by the relevant team. Good, thank you. Right, we move to coffee break and we reconvene at the next session at 25 to the hour.
So, Emmanuel. Emmanuel, are you there? So if you want to test your connection, please do.
Yes, can you hear me?
Yes, we can.
Okay, so it will be okay
So,
for the audio?
yeah, just try to present your screen and let's see if you are able to do so.
Okay, so I try to share the screen.
Yeah, we can see it.
And maybe it's better now? So,
Yes, right now it's in full screen.
okay.
Okay, thank you.
Thank you.
So, Gary, do you want to test also your presentation? Whether you
Yes, if that's okay, I'll just try it now.
we cannot hear you. See?
You can't hear me?
Okay, yeah.
Yeah. Okay. Yeah, I'll just try now.
Yes, you are presenting right now.
Great. Okay. Thank you.
We can see it. Okay, perfect. Thank you.
Thanks, Evold.
So, Miguel, are you there? You want to test also your presentation, whether you are able to share your screen?
It's very useful and it significantly reduces cloud contamination, even if it's not ideal. But at the same time, we are developing and adapting the Bayesian cloud detection method, and we are developing the processing in collaboration and with the help of Chris Merchant. As you can see on the bottom, so you can see an example of Landsat 9 image in the true color mode. Then the radiance at 11 micron with the native cloud mask and with the Bayesian, the first version of the Bayesian cloud mask. So the initial results obtained with SAT9 are very promising and indicate a substantial improvement in cloud discrimination capabilities. For eco-stress, given the noise level and the occasional presence of artifacts, adapting the method will not be straightforward. Another challenge is the occurrence of artifacts, especially for eco-stress mission. So one of the occasional artifacts we have found appear as large-scale structures, as you can see on the figure. At the bottom, on the left-hand side figure. So those large-scale structures contaminate approximately 15% of eco-stress images. These artifacts are due to the solar array absorption under certain conditions of sun satellite geometry. In the eco-stress version 2, the field of view obstruction metadata field is included, but not populated for tiles before 2025, and then can also contain false positives. So because of the phenomenon cannot be reliably predicted using geometry alone, we developed a machine learning solution. Specifically, the net architecture was trained directly on radiance imagery to identify and mask contaminated regions. And this approach has proven highly effective for automated artifact detection. As mentioned, building L1C product necessitates calibration correction. Eco-stress across data as a sequence of overlapping scans generated by the focal plane. This acquisition geometry creates radiometric artifacts and calibration challenges. As you can see here on the right-hand side panel, so you can see a zoom of the radiance in several spectral bands, and so you can see, you can have an idea of the noise and of the overlapping I'm talking about. So in the focal plane, pixels show systematic biases dependent to their X and Y position, and also to temperature. Correcting these artifacts is thus an essential prerequisite before any SST retrieval can be attempted. The previous studies, notably by David Wessey and colleagues, have demonstrated this effect. Due to lack of calibration reference, we implemented a self-calibration approach using homogeneous areas to estimate the systematic relative biases within the focal plane. So you can see in the middle the mean bias lookup table we have generated to correct each scan. So using approximately 4,000 eco-stress images collected during 2 years, we identified homogeneous scenes and estimated systematic pixel and temperature dependent biases. This allowed us to generate three-dimensional lookup tables indexed by a long track and a cross track pixel position and wetness temperature. And we also generate diagnostics for each pixel of the sky. So it should be complemented also with absolute calibration to a reference. And you can see the approach with YASI presented by David Wessey. Applying this correction significantly improves consistency across the images. We also apply the stripping algorithm with parameters adapted to each spectral band. The algorithm is applied scan by scan because of overlapping scans. You can also see an extract zoom of radiance at 11 micron with no correction on the left. The destripping correction applied in the middle and the two corrections applied on the right figure. And the right-hand side figure shows the section for the original radians and for the two corrected fields. So it's not ideal, it should be improved, but and we are currently testing an ENS method, but it's a first step to improve the denoising of radiances from eco-stress. Once level 1C radiances have been generated, the next step is SST retrieval. So we implemented and evaluated 13 linear and nonlinear SST retrieval formulations. Linear formulations are interesting since, for example, and for Trishna, maybe we won't have a first guess everywhere, especially over small lakes and in lagoons or estuaries and complex, over complex shorelines. So the corresponding coefficients are estimated either through satellite matchups with Sentinel-3 observations, with in-pixel homogeneity constraints, or through Ertetov radiative transfer simulations. All the SST are retained for the evaluation step for the validation. And in the distributed versions, we will keep the two best SST products in the final collection. For eco-stress, we have to eliminate the overlaps. The initial method proposed by eco-stress team could mix pixels from one scan to the following scan, increasing the noise. But to overcome this issue, we adopted an elliptical weighted averaging approach. This method is already used operationally for sensors such as MODIS and VIRS and provide more consistent graded products, preventing noise amplification. So to support development and validation activities, we built a large database of Landsat 9 and eco-stress observations. The archive covers several regions of interest, including the Northeast Atlantic, the Mediterranean Sea, French Polynesia, and the region of New Caledonia in the Pacific. Overall, we collected tens of thousands of scenes dating from 2018 to present. All observations are processed according to harmonized level 1C and level 2 standards compatible with GRIS convention. This database forms the foundation of our algorithm development and validation framework. So assessment is a central component of the project as well. So we generated extensive matchup databases with both satellite and in-situ observations using the Felix tool. For satellite comparisons, we use reference sensors, including SLSTR and VIRS. For in-situ validation, we rely on drifting buoys, coastal moorings, and shipborne infrared radiometers. And these matchup datasets provide the basis for evaluating SST retrieval performance. To facilitate systematic evaluation, we also developed a series of diagnostic dashboards. This tool allows us to examine statistical performance metrics, spatial comparisons, dependency analysis, and feature resolution diagnostics. Particular attention is given to the preservation of small-scale thermal variability, which is one of the main advantages of ultra-high resolution observations. These diagnostics allow rapid iteration between algorithm development and performance assessment. So, for example, the top table shows statistics for each SST retrieval algorithms, and at the bottom you can see the bias, that is the estimated SST minus reference versus, for example, the wind speed or the water vapor content or the indices in the fractal. An important objective of Calista is also to facilitate access to data. So we are currently working on the distribution of the product as a stack collections through Ifremer's catalog infrastructure. And you can see here an example of selection of one type via this tool. So to conclude, Calista demonstrate that Landsat 9 and EcoStress observations can be transformed into ultra-high resolution SST products suitable for coastal applications. But there is a lot to do in the future. We developed a complete processing chain covering calibration correction, artifact detection, cloud masking, SST retrieval, validation, and data dissemination. Substantial database and collaborative infrastructure are already operational, providing a solid foundation for future development. But most importantly, Calista serves as a precursor framework for upcoming missions and helps prepare the scientific community for the exploitation of future 50 to 100 meter SST observations. Beyond data production, we established an open virtual research environment. This platform provides shared resources for iterative development of very high resolution SST products, including reference datasets, cross comparison tools, algorithms tuning via Jupyter notebooks, and processing capabilities. The idea is to create a collaborative ecosystem where scientists can test new approaches, assess algorithms, and contribute improvements. We see this environment as a prototype for future collaborative infrastructures supporting missions such as Trisna, LSTM, or Eagle. And several developments are currently underway. These include improved denoising techniques, refined calibration strategies, optimization of SST retrieval algorithms, enhanced cloud detection based on Bayesian method. And so together, these improvements will further increase product quality and scientific value. And thank you for your attention.
So thank you, Emmanuel, for this comprehensive introduction to all the challenges you face with the higher resolution SST. We will have questions after the first three talks before the break. So please stay with us, Emmanuel. Then the next talk is from Guel Mies from São Paulo University on the thermal stress history of South Atlantic reef retrievals, increasing intensity, duration, frequency, and likely undocumented bleaching episodes. So Miguel, can you hear us?
Yes. Can you hear me well?
Thank you. So go on.
Okay. I'm going to share my screen. I would appreciate if you could tell me if you can see my screen.
Sure.
Okay. Can you now see it?
So we see your screen, but now it's in presentation mode. Thank you. Go ahead.
Sure. Thank you. So thank you for having me. This is my first time at GHRSST. Unfortunately, I could not be with you in person today. I'm not a hardcore remote sensing kind of researcher. I'm an oceanographer, actually more focused on the ecology of coral reefs, but I've been using tools that are derived from remote sensing measurements of temperature that have been quite useful for us. So I think I'm going to give a more biological presentation, but focusing on how those tools can be relevant. So I know that William has done some introduction on coral reefs to the audience, but I'm going to go slightly through it again. So coral reefs are quite important ecosystems today because they're the most thermally vulnerable marine ecosystems. So they're the first among all marine ecosystems to decline significantly due to climate change. So they're important indicators. And the reason that these ecosystems are so sensitive is that because they've been evolving across millions of years in relatively stable temperature conditions. So temperature has not varied a lot across the lifetime of coral reefs. So whenever we introduce change, which is what's been happening in the past few decades, several decades actually, they're not really used to that, so they will respond negatively. And the main consequence of thermal stress to corals is a phenomenon called bleaching. Bleaching is defined by the loss of dinoflagellate symbionts, these guys over here, that are found within the cells of corals. So what happens is that these symbionts are actually the first ones to respond to heat stress. And instead of providing corals with carbon, with food, under thermal stress, they stop doing that and start producing reactive oxygen species, which are toxic. So the symbiotic partner, instead of being, a positive force within the coral, now it's a negative force. So the adaptive response of the coral host is to expel those symbionts. But because they rely on the symbionts for energy, prolonged loss without this prolonged loss, symbiont loss, and prolonged periods without the symbionts will produce an energetic deficit. So they'll starve to death. It's called bleaching because the coral's tissue will turn transparent, and you can see the white skeleton underneath the translucent tissue. But bleached corals are still alive. They're not really doing that well. They're close to death, but they're still alive. But bleaching, nonetheless, will produce a lot of coral mortality. And we have been seeing a severe level of destruction of coral reefs globally, largely associated with the El Nino Southern Oscillation. Every time there's the warm phase of El Nino Southern Oscillation, the coral reefs of the world will face what it's called a global bleaching event, where roughly around the same period, corals in the Atlantic, Indian, and Pacific Oceans the majority of them will bleach. And we faced 4 of those. The first one was in 1997, then we had another one in 2009. We had a really strong one, the third global bleaching event, lasting for 3 years between 2014 and 2017, and we've just finished going through the 4th global bleaching event in 2023 to 2025. But without being as if that's not bad enough, we have what we call local bleaching events or regional bleaching events that are not connected to the El Nino, and they're just manifesting in between global bleaching events. So it is a tremendous level of thermal stress and frequency of thermal stress that these environments have been subjected to. As a consequence, we have lost about 60% of all corals that we had in the early 1990s. So in about 30 years, we were able, with global warming, to kill more than half of the world's corals. Because of the severity of bleaching, long-term monitoring programs have been established in several parts across the globe, mostly the Caribbean and the Indo-Pacific. But in the South Atlantic, where I come from, we've been lagging behind. So there were no long-term monitoring programs established until about 6 to 7 years ago, I would say. But the South Atlantic is a very unique reef system because we have the Amazon River discharge onto the Brazilian continental shelf, which provides almost like a barrier that restricts gene flow and migration of reef organisms between the Caribbean and the South Atlantic. And with not only the Amazon, but several other rivers discharging onto the continental shelf, we have very unique oceanographic conditions. So we have lots of turbidity, we have much higher nutrient concentration. So that unique setting caused for the South Atlantic reef fauna to be very low in diversity because it's so adverse for corals to develop that only stronger species were able to develop, but with a lot of endemism because of the partial isolation that the South Atlantic province faces. So it's a very interesting and unique reef system that is entirely different from what you would expect comparing to, the Caribbean or the Indo-Pacific, which are so well lit and clear water and so on. And in Brazil, bleaching was truly not adequately monitored until 2015. We had very sparse bleaching documentation across the coast until then, when we had the third global bleaching event, which produced a relevant amount of bleaching, but not a lot of mortality. And then in general, the scientific community started to pay attention to that. So there was not a lot of field data until 2015 or later. So whatever happened in the Brazilian coast before then, nobody knew. So, bleaching was being extensively documented in the Caribbean, in the Pacific, severe mortality, but nobody was there checking what was going out in the field here in Brazil in the South Atlantic. So that's when I resorted to the tools that you guys at GHRSST are so experts on, which is satellite-derived data from the past to reconstruct past thermal stress events that have manifested in different areas of the world. So we were particularly interested in DHW. I presume that's been explained in the previous talks, which is a very relevant metric, which is the accumulation of thermal anomalies exceeding the maximum monthly mean over the previous 3 months. And when we have about 4-degree heating weeks, in general, you will have mass bleaching. Beyond 8-degree heating weeks, you will actually face mass mortality. Of course, that varies regionally a lot, but it's a fairly good predictor. So can we use that? That's what we asked ourselves. Can we use that to reconstruct past bleaching episodes in the South Atlantic? And can we tell whether thermal stress episodes are increasing in intensity, duration, and frequency? So what we did, we selected 33 reef sites across the South Atlantic that are very, relevant in coral cover. So you can see they're distributed across the South Atlantic into 5 distinctive regions: the North, the Northeast, the East, and the South of South America, the Oceanic Islands, and the coast, the Atlantic coast of Africa. So we collected DHW data from the NOAA database for the last 40 years for each of those reef sites. And whenever we detected DHW higher than 4-degree heating weeks, we identified that as a very likely bleaching episode that took place. Then we did some basic summary statistics on the number of thermal stress episodes that each site experienced, the number of days under thermal stress, and so on. And we were focused on 3 specific variables. First of all, the intensity of thermal stress, which was defined as the maximum DHW value recorded during a given thermal stress episode. The duration of thermal stress was the number of continuous days in which DHW was higher than 4 and that we had 1 degree or more anomalies manifesting. And the frequency was the number of days between thermal stress episodes. We did generalized linear models to evaluate then whether intensity, duration, and frequency are becoming more common over time, whether they're increasing over time. And what did we find was quite interesting. In the 1980s, we had about 2 thermal stress episodes per year across all sites. That jumped to about 3 across the 1990s and the 2000s. In the 2010s, we jumped to 8.1 episodes per year, and in this decade, current decade, 15 episodes per year. So it's clearly on the rise. Some of the
So,
south.
sorry to interrupt, but just to tell you that I have 2 minutes left.
Yes, some of the south sides face more than 20 thermal stress episodes, so it's really strong. While the oceanic islands in Africa experienced the least number of episodes. So, but what was interesting is that we detected multiple thermal stress episodes for sites for which there are no bleaching records. And here we can see that the intensity of thermal stress is clearly on the rise. So you can see across all regions, thermal stress is becoming more intense. Temperatures are getting higher. The accumulation of anomalies are getting higher. As for duration, the same here. So they're lasting for longer periods, up to now 50, 60 days of thermal stress, which is a lot for these environments. And the frequency is reducing for all regions except for Africa. There's a reason for that, but I won't get into detail. But except for Africa, every region the frequency is reducing. That means that thermal stress episodes are getting closer to each other. This tells us, so the y-axis here is the duration of thermal stress, and the x-axis is intensity. So you can see clearly that the more to the top and to the right, in general, both duration and intensity are getting higher. And this is clearly what you can see in the recent decades. This I'll go through. This is just latitudinal patterns. And what does this mean? Like I said, multiple thermal stress episodes where intense bleaching likely occurred were detected, but these were never documented in the field. One of the reef sites that is so important, there's only one bleaching episode documented in 1998. We detected multiple bleachings after that nobody was there in the field because it's a remote and difficult to reach area, but that has been bleaching much more than that. In fact, we just detected this year that one of the species that's only found there has gone extinct. We lost a coral species that's endemic to that area. Likewise, one of the areas in Brazil that we've only visited in 2020, nobody had ever been diving there until then. We revealed that bleaching has taken place several years, and only twice there were expeditions there. In 2020, we were there, we detected bleaching, and again in 2024, but bleaching took place in many other years. What made us quite happy, I'm close to the end now, is that our data was validated at Abrolhos. Abrolhos are the most important reefs in Brazil and the only site that has been continuously monitored since the early 90s. And only 3 episodes were detected in our data, bleaching episodes, and those 3 episodes match perfectly with what has been observed in the field. So what we can conclude is that there's a clear increase in the intensity and duration of thermal stress across the South Atlantic, as well as increase in frequency along the South American coast and the oceanic islands. And we have experienced much more bleaching than we have detected. So the kind of tool that DHW and NOAA provide is excellent for us to rebuild the past in areas where we haven't been able to go into the field. To conclude, the findings of this presentation are in detail can be found at an article we published last year in Global Change Biology, an article to which William is a part of. So that's it. I'm glad to be here. Thank you for having me. I know I'm a bit, a different species, and I appreciate you having me and accepting me here. Thank you.
So thank you, Miguel, for this important work on documenting a region previously not so much attention to. We will come back with questions after the next talk.
Sure.
So then it's over to Gary Corlett at EUMETSAT and a quite different subject. Self-consistency of global and regional high latitude marine skin surface temperature from the Copernicus SLSTR radiometer.
Thank you, Steiner. Hello, everybody. Yeah, so I'm Gary Corlett. I'm working in the surface temperature radiometry group at EUMETSAT, along with Anne and Igor. And we recently introduced a new high latitude sea and sea ice surface temperature product. And this talk will focus on looking at how consistent it is with our existing global sea surface temperature product. For those of you not familiar, the sea and land surface temperature radiometer is launched by Copernicus, the first one in February 2016, with the sister S3B launched in April 28. And these are dual view self-calibrated infrared radiometers that continue the ATSR series. So the dual view offering an improved atmospheric correction. They also have 2 onboard black bodies to improve the radiometry, and we have very low noise detectors, which are optimized for SST retrievals. The next in the series, SLSTRC, is expected to be launched later this year, and it will replace SLSTRA in the operational configuration, which we expect to occur in the middle of next year. We've recently gone operational with our Collection 4 dataset, and as I mentioned, this includes this new IST product, which at the moment is not operational, but we will be releasing it openly on Thursday. So the SST product, I won't focus on the retrieval itself. The experts are in the room, so I will defer questions to them. To just note that we provide data in both real time and an offline product, which are now going to be both available in 3-minute granules. So if you were familiar previously with the full orbit products from Collection 4 onwards, these no longer exist. A reminder as always that SLSTR provides SST skin. However, in the new Collection 4 products, we do now provide an SST depth estimate following the methods demonstrated in the ESA SST CCI project. And this depth is for 20 centimeters to be equivalent to drifting buoys. For cloud masking, we actually use the Bayesian clear sky. So we're not trying to identify cloud, we're trying to identify clear sky. This has recently been updated to include an improved pre-processing step. And you can see the paper led by Claire Bulgin on this for more details. The only change that we've made since then is we do now add channel S5 at high latitudes, and this is really to help distinguish sea ice. As part of the Collection 4, we've introduced a new ice flag, and that's part of the evaluation we're going to be doing now. And this is work based from the ATSR reprocessing for climate project, and this is work summarized by and led by Owen. So to note that in the surface classification I'm going to show you, the priority is given as initially open water, then we're going to identify what we think is ice, and then finally the remainder is going to be cloud. So the new high latitude product, which is available if the product contains a latitude above 50 degrees north and south in both hemispheres, combines both temperature estimates over sea ice and open water. And it's in a GHRSST-like format at the moment. And of course, this is subject to the ongoing discussions for GDS3. The algorithms themselves were defined by Bettner DMI. This is work led by Steiner and by Gorm. And we have 2 different ones for both. The nadir view is a split, traditional, more split window based. And then following recommendations from many people, including Andy Harris, who's there at the meeting, for the dual view, we only actually use the 11 micron channel, but this is using both the nadir view and the oblique view. In this case, for cloud masking, we are using the PPS cloud masking scheme. This offers several different products you can combine to create an overall assessment if you think the pixel is cloudy or not. So in this particular case, the surface classification is different to the SST product, where we first have an indicator if we think it's cloudy, then we have an indicator if we think it contains ice, and then finally, if it's neither of those, it must be open water. So we're going to evaluate not only to see whether they're consistent, but we've got 2 completely different approaches to the data. So what I'm going to show you now are some examples. So each of these slides will have 6 plots, as you can see. So the upper left is an RGB image from 3 visible channels in the daytime. And what you notice clearly is you can see land predominantly, if it's clear, will be a slight red tinge because of the channel combinations. Ice will generally appear to be a slight light blue color, and clouds and snow will be more white. The bottom left is a similar now, but this is an RGB from the thermal channels, and in which case the 3.7 channel is the red channel, And as you can see, that this is clearly giving a lot of information, especially on clouds. And this is in the daytime, so something that we could consider, certainly I think at high latitudes, is much more daytime use of the 3.7 channel. In the middle plots at the top left is the surface classification now from the WST product, and at the bottom is from the IST product. And overall, as you can see, there's generally good agreement. So we can see in the dark blue, the open water, in the cyan color, the ice is generally the same. There are some noticeable differences, particularly if you can, hopefully you can see my mouse in this region, but this is a very simple surface classification that has no knowledge of clouds at the moment. So the fact that there may be some thin cloud that's affecting this is to be expected. The top right shows you where they disagree. So if it'll either between the two, and overall, as you can see, we're just focusing mainly on the clear sky ocean at the moment. There's very good agreement between the two for this particular product. It's generally cases between ice and cloud where we start to see differences. And the bottom right is the difference between the surface temperatures only for the clear sky water pixels. So in this particular example, we've got quite good agreement. The second example, again, similar sort of plots. So you can see where we will land, you can see where the sea ice generally exists, because it's a slight blue tinge to it, and you can see some very clear cloud. And then again, overall, between the two products, we're seeing very good agreement in what we're classifying as open water. If anything, the IST product at the moment has a tendency to underestimate what we think is ice. We see generally slightly more open water from the IST product. And again, looking at the differences, we're getting very, very low, a good agreement. Of course, there are cases where the agreement is not good, and this is one particular example. This is where we're now moving towards twilight, so we've got slightly lower radiances, and you can see now the imagery, the blue in particular, is much more bold than it was in the previous one, and the thermal structures are different as well. And in this particular example, the agreement is quite good, apart from we seem to have something at the edge of the swath. Yeah, you can see now in the bottom plot in the SST difference, you can see on the right-hand side of the swath, we are now seeing some larger differences. Now, you would ordinarily think this may be to do with view zenith angle, but actually the way the SLSTR swath works, the extreme zenith angles are to the left of the image, and it may be that there is some view zenith angle dependence, but we certainly wouldn't expect it this side of the image. So we have a little bit of work to do to better understand why these differences are occurring. So to summarize the findings so far, so I have to give a caveat that at the moment we've only looked at a very limited test data set. Our product was slightly delayed in release. So as I said, the IST product will only be going operational on Thursday, and we expect to be able to do a lot more routine monitoring of these statistics to get a better example. However, there is good large-scale agreement for open water. I struggled to come up with an estimate of the percentage, because we in many cases the agreement is close to 99%. But as I said, we do see these cases where the agreement is not as good. Ice water discrimination issues where they occur, unsurprisingly, are occurring where we mainly have these mixed pixels, where there is some uncertainty if the pixel is ice or water. We do see some larger scale disagreements, but these are generally ice cloud and not ice water. We do also note in some examples, I've not shown them here, that where we have very small inlets and regions close to the coast, we get much larger agreement. And I think this is due to limitations in the prior, which is generally at a much coarser resolution than the 1 kilometer data from SLSTR. The IST product generally seems to have more pixels classed as open water. And as I mentioned, the two classification methods are slightly differently. So this is something we will need to look in the cloud mask to see why we're getting the different results. However, it's not impacting the actual SSTs. I haven't looked too much at the ISTs yet, but we don't see any difference in the SSTs, and we are seeing this issue towards twilight. However, we have got some examples now where it's the reverse, and the IST product now has ice classed as open water, and these ones are where I showed you at the edge of the swath, which may have something to do with view angle, or it may be again due to very low radiances at the higher latitudes, and this is something to work from. However, the IST flag looks to be performing well. We do see some overflagging of ice over particularly thin clouds, but as I said, this test has nothing to do, has no knowledge of clouds at all at the moment. And so from a first go at trying to distinguish and to get consistency between the two products, we're quite pleased with how it's performing, and we'll refine it in future tuning with our algorithm experts. There were some small differences in the land mask. We do have a slightly different land sea mask as a basic mask between the two products, and that's something we'll reconsider in future tuning of the data. So to conclude, so we have two products now available from the Copernicus SLSTR. So we have a global sea surface temperature product and the regional high latitude sea SST and IST product, where the IST is provided only over surfaces we think are sea ice. The collection 4, compared to the data previously, has a number of additional advantages, including improvements in coastal areas. We have the SST depth, and also you now have access to the full nadir grid, as we've shown in presentations at previous meeting. The new combined product is available again at the moment. It's only for the marine domain only, and it'll provide either SST, IST, or a mixture if we think the pixel cannot be uniquely determined as either ice or water. And at the moment, we are using a different approach to cloud identification. We're using the EUMETSAT NWCSAF PPS cloud mask. The WST product was operational on the 11th of June, and as I've mentioned, IST will be operational on the 25th, and at some point there will be a full reprocessing. So overall, we're seeing pretty good agreement. It's generally over 90%. As I said, most cases that we looked at, that it's, in fact, the agreement is very good. It's over 99% in being able to identify open water and sea ice. There is a caveat, though, that, as I said, we've only looked at a limited number of test cases, but from comparing two different methods and two different approaches, the results are quite pleasing. Coastal areas do require some further work, and this really is due to, unfortunate at the moment, we have limitations in available prior, particularly sea ice concentration and both NWP, and this is just because of the nature of the limit of the products compared to the 1 kilometer data we're using. We do need to reconsider our IST land sea mask, and that's something we will talk with Steiner Gorman and the experts at METNO and DMI to improve. And then finally, the next steps, we will expand the scope of the analysis and try to do real-time, more qualitative analysis of these different statistics. And of course, we'll now shift the focus to now look at clear sky, sea ice pixels, as well as the open ocean. And with that, if you be happy to take any questions in the discussion later. Thank you for your attention.
So thank you, Gary. And then let's open the floor for questions on all the three presentations. Anyone? Oh, yeah, Chris, thank you.
I have a question for Emmanuel. Thanks for your presentation, Emmanuel, and it's great to see the Callista tool and your openness to collaborations. I think this is something we should all, those of us who work on retrievals or are interested in ultra high resolution, should be thinking about collaborating with you through this tool. It looks really interesting. I had a question about your SST retrievals that you plan. You showed that you're going to be examining coefficient-based retrievals. One of the things that is of interest, of course, is the high gradients, the SST gradients at high resolution. And as we've known for a number of years, sometimes coefficient-based retrievals suppress the strength of the gradients. So I wonder if you're planning to assess that.
Yes, thank you, Chris. Yes, we plan to assess that, and we have already seen some, for example, for some of the algorithms we have tested, the statistics are very good. But finally, and especially for nonlinear algorithms, when we use first guess, which is also, of course, coarser than in terms of resolution than the observations, it has an effect on the final SST retrieval and on the gradient we can obtain. So I think we have a lot to do on this part of the validation, since finally we can have very nice statistics, or maybe the mean, the bias is very good. It's close to 0.0, but in terms of standard deviation, it can be higher than other algorithms, etc. So we have a lot of things to check, and yes, it's a problem. It's also, of course, we have to cope with a high level of noise, especially with eco-stress observations, but also with Landsat 9, even if it's the noise is less present. So yes, it's an important part of the validation and of the work to do to deliver very useful high resolution observation. I don't know if I answered your question, Chris. It's okay?
Yes, thank you. Yes, I'm just happy you're looking at the gradients as well as the absolutes. Yes.
Okay, so Christina, then.
There is one in the. I have a question, but I can wait. There is one in the chat. I don't know. It might be Helen, not sure, because it says some user, but it was Helen before. Helen, can you hear us? Can you ask the question directly to Gary? Otherwise, I will read it. Okay, I might read it if. No. Yeah. You're coming, I think.
Oh, yes. I thought, hi, Gary was online, so I thought I'd stick it in the chat. But yeah, it was just the quick question of whether the new SLST product would be available over the Antarctic in real time, because I know that the modelers at the Bureau and elsewhere in Australia are really keen to get an accurate ice temperature around Antarctica for their models. Thank you.
Hi, Alan. Nice to see you. Yes, so the product is available in both hemispheres. So it'll be indicated in the product with SH as part of the file name, so you know which ones to take if you only want the Southern Hemisphere ones. It's just the examples I showed where we're focused on the Arctic, because that's where most of our validation results are at the moment. But we are looking at Antarctica as well as the region around there, as well as the Arctic.
And is it going to be in real time?
Yes, it's available in near real time. Yeah.
Right now?
Yeah, from Thursday.
Fantastic. I don't know if you can send me the link, otherwise I'll search for it.
Yeah, sure, we can send you details.
I can pass it on to my Bureau colleagues, because I think they might be very interested. Thank you.
Yeah, no problem. Thank you.
And then just a comment to you, Helen. to pass on to your colleagues if they have any funding or any wish to see the quality of these products in the Antarctic. Please consider any validation campaign in the Antarctic.
I am retired, but I will pass it on to them. Thank you.
Thank you. So I think there was a question in the back. Oh, yeah. Yeah, microphone, please.
Hi, I'm Angela Landolfi, working at the National Research Council in Rome, and I have a question for the second talk regarding the coral bleaching. So I'm wondering if there are other parameters that can affect coral bleaching, something like pH. And I'm asking this question because at CNR we have developed a combined atlas of both marine heat waves and ocean acidification events, extreme events. So I think that can be useful in that direction. So yeah, thanks for your talk.
Thank you. Thank you for the question. So there are many causes to bleaching. The most common is by far thermal stress, but you can have bleaching associated with pollution, with disease, and so on. Ocean acidification and pH reduction, however, do not promote bleaching. Actually, because bleaching is actually something that starts with the symbiont, the algae that is associated with corals. A reduction in pH, which is associated with higher concentration of CO2 in the water, will actually benefit the algae very slightly. So would that mean that ocean acidification is good for corals? Well, no, because on the other hand, for the coral, it's a big problem because the CO2 will react with the water to produce hydrogen ions, and those ions will react with bicarbonate ions, with carbonate ions to form bicarbonate ions. So it's actually sequestering carbonate ions from the seawater, and that's a big problem because corals produce skeletons of calcium carbonate. So one of the elements for calcification becomes rarer. So acidification will actually help the symbiont a little bit, but will cause a lot of problems to the coral, but it will not bleach because bleaching, by definition, is the loss of the symbiont or the photosynthetic pigments of the symbiont. So because there's no symbiont loss, ocean acidification will not produce bleaching. It's another dark side of climate change, but not associated with bleaching.
Thank you. So yeah, I think Pallavi was first, and we have time for those two last questions.
Yeah, so I have a question for Miguel again for the coral stress. So thanks, and it was really great to get perspective from the biological world.
I'm sorry to interrupt. The volume is a bit low.
Hello,
Yeah.
can you hear me now?
Oh yeah, much better. Thank you.
Okay, thank you. So my question is about bleaching data. So you said when the corals are bleached, that doesn't mean they are dead. So what is the reverse of the bleaching? So it happens in years, decades, or centuries. What is the time scale? And then the other question is, you showed some numbers decade-wise, how many reefs were bleached. So was that a repetitive survey on the same reefs, or it was completely different regions? They were surveyed in different decades.
So those are good questions. So yeah, so bleaching when the coral is bleached, he's still alive. In general, severe bleaching will produce severe mortality, but corals can recover from bleaching. If they don't get to die, of course, they can recover. And they will recover by associating with symbionts that are there drifting in the water. But the time frame for regaining their color and their health is very variable. If it can take from several weeks to 6 months up to a year. I've seen the same species of coral bleach entirely and then recover their color within a month, and the same species in another area, another latitude take about 12 months. So it's very context depending. But we're talking the scale of a few months usually. As for whether we were serving reefs repeatedly, not sure I follow entirely the question, but in our case, there was only one reef that we were there in the field constantly throughout the 90s, 2000s, 2010s, and 2020s. So those reefs were important because they validated our findings, the remote sensing findings, because the remote sensing data only detected 3 bleaching episodes at that site. And when we were serving the same reefs consistently, we only detected those same 3 bleaching events, perfectly matching what the remote sensing data produced when the bleaching manifested. Now, the other reefs, there were very poor, very few investigations, and only in the past 10 years or so. So whatever happened before 2015, nobody knew. So this is why that kind of tool is very important for us to reconstruct the past thermal stress in areas where we weren't there to assess the effects of thermal stress. So it was very relevant to us. We were under the impression that we hadn't had severe thermal stress or heat waves in our reefs in the 19s or 2000s. Now we can see that we're completely wrong. There are many thermal stress and heat waves, and we may have lost more corals than we know because there was no one there to check. So we know that there was thermal stress and most likely bleaching, but the mortality, nobody was there to document. So it's a very good way to look into the past. We're getting very new insights on how to conserve and preserve these reefs based on that data. I'm sorry, did I answer the question?
No, yeah, that's good. Yeah, thank you. That was helpful.
Thank you.
Thank you, Miguel. We are running a bit late, but I think Christina has the last.
It's fine.
moment.
I can send the question by email or as you wish. It's a quick question otherwise, as you wish.
Well, up to.
Okay, it's a quick question for Emmanuel. Sorry, I might miss the details, and I'm sure that you comment on that. But I just wanted to ask if you can just provide more details on the data that are available on the Ifremer catalog from Callisto. Is that kind of collocated data of SST and the visible data as the one that you use for showing the cloud, the enhanced cloud mask detection? I don't know if it's. So I just wanted to know which are the data available from Callisto.
The data that will be available are the L2 products, so containing the SST and the variables that are provided also by the producer, so in the original files from EcoStress or Landsat, for example. And we have added also the cloud mask I was talking about. So the original, the native cloud mask, and then what we extracted from the geostationary product. So you can have these variables in the files. I'm not sure I got your point.
My point is that it would be really useful for us at ICM to test our algorithm to retrieve the cloud mask, the same figures that you were using for testing yours. So you were comparing the Bayesian mask, and then you were comparing with a visible image to see if you were improving or not. I think you had a slide like that.
Yes, because for the moment we are working on Landsat 9 data for testing the Bayesian cloud mask. So we also have observations in the visible part of the spectrum. So we use that. We have also tested other masks than F mask, which is the original mask provided by Landsat, by USGS, and but those masks use the visible informations. So it's a way to validate the cloud mask you are developing with only the thermal infrared observations. It's easier to start with daytime observations when you have also visible observations. So it's possible with Landsat, but it's not possible for EcoStress unless having other observations from other missions that are collocated with your image. But it's yes, okay. The cloud mask we add from the geostationary observation. It's good for our first version and for validation, etc. But some clouds can evolve very fast, so sometimes you have a mismatch between the cloudy parts of the EcoStress image and what we had from the geostationary satellite.
Okay, thank you. Yeah, I will write you. Okay.
Yeah.
Thanks.
So thank you for your patience, and thank you to all presenters. Sort of taking a bit of your break. Now we break for coffee, and maybe not half an hour, but how long will the break be? Should we try to catch up a bit? Yeah, so we reconvene at 5 o'clock. Yeah, so a quarter of an hour break, and then there's 2 more presentations, and then some GHRSST priority discussions. Yeah, thank you. Okay, everybody, let's try to focus a bit more. We are coming to the last part of the longest day here at GHRSST, at least in terms of number of presentations. We have 2 more presentations in session 3, and then questions and GRIS priorities. So first, let's give the word to Kohei Mitsubata and a combination of marine heat waves and sea ice. That sounds interesting.
Thank you. My name is Kohei Mitsubata from Tokyo University of Marine Science and Technology. Nice to meet you. Today I'm going to talk to you about marine heat wave things around the East Antarctica. This figure is GHRSST anomaly, January 2026. The Totten ice shelf is there. Right now, in the East Antarctica, Totten ice shelf is melting drastically. And there is very, very high SST anomaly. And at that time, I was there, and I couldn't go to the Southern Ocean. Almost every year I went to the Southern Ocean, but our ship had an engine failure. But icebreaker Shirase, Japanese icebreaker Shirase, go to there, and Ono-san on the icebreaker Shirase took photo like this, very warm sea surface out there. So this photo made me start this kind of investigation, because a bunch of heat is there. That means maybe have an impact on the lateral melting of sea ice and ice shelf as well. And this kind of phenomena is not a rare case. In 2022, the Aoki et al. Already reported, they are not saying that marine heat wave, but very high SST found at the ice front of the Ameri ice shelf. It's a Pritz Bay. It's the same East Antarctica. So, okay, I would like to start investigate about the marine heat wave. But that this area is, there's a bunch of sea ice out there. So that usually the Heatwaves et al. Framework, you need daily climatology and past 90 percentile data from the January 1st to the December 31st. But there's a sea ice. So, this is challenging, how to investigate the marine heat wave in this area. Okay, the key question is, can OISST, the based marine heat wave detection, capture the Antarctic coastal warm anomalies, and also what additional coastal scale information is resolved by the GHRSST, the MER product? And also, when and where does OISST underestimate coastal marine heat wave frequency or severity? In this study, because the resolution is different, so I want to compare the OISST data and also GHRSST MER data. And then using the both data set, try to detect marine heat wave in the East Antarctica. And also, it's a pretty fresh data. The XCTD data were obtained by the icebreaker Shirase in the last January. So I will use this data to check that high SST signal is real or not. And I need to say this. The common baseline for product comparison is 2003 to 2014, because I want to compare the OISST and GHRSST. So I'm not focusing on the long-term trend things. Okay. I think the people in this room already know the definition of marine heat wave things. I don't want to go detail, but just I want to say, applying the Heatwaves et al. Framework, and that linear trend was removed. And there, as I said, there are a bunch of sea ice. So just I would like to focus on the December to February, the open water period, and then try to investigate the marine heat wave state. But I have actually, I don't understand why 5 days. 5 days doesn't mean anything, right? Okay, 4-day duration can be ignored. I don't think so. So just at the first step, just ignore, just forget about 5-day limitation, and then following this kind of framework, just maybe you guys know about the calculate climatology and the 90th percentile, and then try to categorize the marine heat wave. All right, this is the result. Using the ORSST, of course, we could estimate the marine heat wave category map. Left-hand side is the baseline period from the 2003 to 2014. And right-hand side is category between the 2015 to 2026. And OISSC detect a broad shift toward stronger marine heat wave state in 2015-2026 relative to the baseline period. The next question is how much coastal and ISH structure is smooth at the 0.25 resolution or OISST resolution. This is a result. Using the GHRSST MUR product, of course, same method is applied, and then categorize the marine heat wave. The left-hand side, same, the baseline period, and right-hand side is, of course, a marine heat wave category between 2015 to 2026. Using the same, the 2003 to 2014 baseline, the GHRSST shows a shift towards strong, severe, and locally extreme marine heat wave state in 15 to 2026. And big difference, this one is OISST, and this one is GHRSST. The big difference is around the coastal area. The GHRSST can detect fine scale and severe marine heat wave area. And right now, I'm comparing the OISST product and GHRSST. It's showing the frequency of the category greater than 2. I mean the stronger or higher. And these ones, the OISST, the base OISST and GHRSST and difference. And upper panel shows 2019, and then this one is 2026. 2026, both OISST and GHRSST can detect extreme marine heat wave around the Totten area. I should say that here, the Pritz Bay, Davis Sea, and Vincent's Bay, and Totten area, and also the Cook Ice Shelf area. Okay, so the broad pattern is very similar, but coastal differences remained, and the difference shows a positive value indicate where the GHRSST detect more strong category, marine heat wave category frequency than OISST. And here is a frequency of the category greater than 2, that a time series of the category, frequency of category greater than 2. The blue line shows the OISST, and the red line is showing the GHRSST result. Basically, the variability is same. And so the timing is broadly consistent between OISST and GHRSST. But look at the Pritz Bay, Davis Sea, Vincent's Bay, and sometimes Totten area. Often shows the GHRSST often shows a larger category 2 frequency during the strong coastal marine heat wave years, except for the Cook area. So this product differences are region dependent, but GHRSST is showing the more higher, a stronger marine heat wave state. Okay, and this one is showing the OISST missed hotspot fraction, the HJ. is just percentage of GHRSST pixels with frequent category greater than 2 marine heat wave, where the OISST remains below the same frequency threshold. So in short, that it's a reddish color means the OISST misses the marine heat wave hotspot around the coastal area. Okay, and this one is a brand new result. As I said, icebreaker shows they go there, and then conducted a bunch of XCTD observation. And based on the GHRSST data, we divided into two regions. The triangle region is upper tercile, is greater than 1.62 degrees Celsius. And blue circle area is a lower tercile. It's less than 1.35 degrees Celsius. And the interesting thing is that this triangle area, its XCTD profile shows warm surface layer and saline waters. All right. So those results suggest us that those water is coming from the basin area. All right. It's transported from the basin to the shelf. And also this warm layer is very thick, greater than 60 meters of depth. It's not just surface event. It's actually a bunch of heat is accumulated in the surface layer. And actually, basically, I'm using the dynamic ocean topography, the satellite altimeter data set, and showing the circulation field, and the background color shows the GHRSST data set, and there's a clockwise circulation is bringing the warm water from the basin to the shelf. So, so what I would say is, okay, 2 minutes. What I would say is that this marine heat wave thing is, of course, that it's solar radiation is important, but the warm water is bringing from the basin to the shelf. This kind of phenomena is also important. Even same solar radiation, that the warm water region is easily become the marine heat wave area. That's what I want to say. And yeah, and looks like I have time. I said I forget about 5-day limitation, but actually my result says the detected marine heat wave phenomena is almost 70% is more than 5 days. All right. So our message is here. The OISST capture broad Antarctic marine heat wave severity changes, and GHRSST resolved the coastal and ice age marine heat wave hotspot, but smoothed by the OISST grid. And all the same 0.25 grid, OISST and GHRSST show similar timing, similar variability, but different coastal marine heat wave amplitude. And some coastal category greater than 2 hotspot occur at spatial scales that are not fully resolved by OISST. So not only in the Antarctic area, maybe the Arctic Ocean as well. In the coral region, if we want to detect the marine heat wave things, maybe we need a high resolution SST product. Okay, I want to finish here. Okay.
So thank you for your presentation about marine heat waves in its unusual region. We'll get back to questions after Joanna's talk, which will be on assessing SST in the North and Baltic Sea using GRIS-compliant SST products from the Copernicus Marine Service.
Thank you. Good afternoon. I'm the last one. I will try to keep it light and simple. So this is, yeah, thanks, Chris. Good nudging. So this is a combined effort from many colleagues, but the idea is to show you a bit what we are doing when we are taking GRIST products and making other GRIST products for the North and the Baltic Sea. I've shown that slide yesterday on a different context. So we are a production unit for the Copernicus Marine Service for the sea surface temperature thematic assembly center, for which we produce regional products for. I'm sorry, I'm trying to find the mouse there. You cannot see it maybe. Anyway, the left side, North Sea, Baltic Sea, this is where I'm going to focus. It's SST only products that I'm going to be talking about. While for the CI stack, we make combined sea surface temperature. Thank you. Thanks. It's fine, it's fine. Yeah, thank you. For the right-hand side, it's for the Arctic Ocean, we make combined sea surface and CI surface temperature products. We don't do that for the Baltic. I'm not talking about this today. So there's a range of products we have on a near real-time basis, level 3, super collated, and level 4, daily analysis and diurnal analysis. And we also have some multi-year products ranging from going back from 1982 up to today. This is a schematic of the processing system. So essentially, we take greased products at level 2 normally, and then we use sea ice concentration for the northern part of the Baltic Sea to identify during winter time where we don't have actual SSTs. And over there, we do not calculate, obviously, an SST. We use the sea ice concentration to mask that out. And then we pre-process all the level 2 data into the level 3 super collated product, which is also released. And then we apply some optimal interpolation to provide the OI, the level 4 gap-free SST. And this is about to go away. I'm going to talk more about that later on, in the end, actually. There's some validation going on, and you can see some of the statistics are pretty standard. They haven't been changing much in time. There's in the table up here, you see the validation for the near real-time product. We've got a big issue with in situ observations, especially in the Baltic. There's no drifters, pretty much nothing. So it's very rare to get a long-term validation. For the lower table, it's the multi-year product. So for that, we got a better matchup database. And then on the right-hand side, you see some examples of when we bin the in situ to level 4 matchups into bins of 0.1 by 0.1 degree. And these metrics are from the multi-year product, which we actually reprocessed last year using the CCI version 3 input data. Some of the new things we did last year are related to ingesting VIRS on NOAA 21. And this is an example of the impact it had on our systems. And the nice thing to see is on the left-hand side here, you see the input data we have only from VIRS on NOAA 20 for a specific date on the 2nd of October 2023. And then the right-hand side shows the actual use of both NOAA 20 and NOAA 21. So we had the test period between March and December 23 to do this. And essentially what we did is that we rerun our near real-time chain, ingesting also NOAA 21, and then compared with our standard product. And for that, we used the standard comparison methods. You see in the table, we have some validation statistics with different types of buoys. The main message is that we didn't see a major impact in the validation metrics, but we had obviously more observations in our level 3 super collated product, which means then less OI going on to fill gaps, because there are less gaps potentially. About more recent things, and this switch from collection 3 to collection 4 SLSTR. We can't really do anything about it. We just have to switch, but we did an assessment of what the impact would be on our production system. And essentially, we used the test period from March to April this year, where we got the collection 4 data, and we also have the collection 3 data, and we matched those up. This is simply SLSTR to SLSTR. There's no ingestion in our level 4 going on here. And we collocated the files and the area of interest, and we calculated some basic mean bias and standard deviation. The left-hand side shows the mean bias. The blue is the actual bias line, and every dot represents a match-up file. So it's the average of the differences in the points in that file. The yellow line shows the number of points used for the estimation of that value. The right-hand side shows the standard deviation for that file. And essentially, I don't know if they are very easy to read. The bias goes from minus 0.1 to 0.1 or 2, but it's for outlier values. We have quite good over 0 biases, and the standard deviation is quite low, between 0 and 0.2, around 0.1, I would say, and the outliers align more with the cases where we had fewer points to collocate. On future activities, and it's been mentioned a bit earlier yesterday, we were actually looking into ingesting AMSAR2 in our systems, but we are waiting until AMSAR3 becomes operationally available. So we've made some tests using AMSAR2, validating the standard product with some in situ observations, and these are shown on the table. And then testing also some different ingestion strategies of how the passive microwave observations are going to be used prior to our optimal interpolation. And what you see in down here is our level 3 supercollated product using only our standard infrared GHRSST products. And then on the top here, you see 2 different ingestion techniques for the passive microwave, either using a 5-kilometer radius around its point or a 10-kilometer radius. So you can see that the Baltic, where we normally have cloudy conditions and no good infrared coverage, starts to fill in. We will do some more tests using actually AMSAR3 data when they become available before we move further with this activity. This is also quite preliminary. We are also looking to ingest MTG FCI, which is currently on a pre-operational status, as we heard yesterday. And this is an example of how it looks today. Actually, the date is at some point a month ago. January 26. On the left-hand side is plots from Meteosat 12 versus the right-hand side, which is 10, which is the standard product we ingest. The top panels are the quality level pixels, and then the bottom panels are the actual SSTs. So essentially, what we are seeing on a preliminary checkup is that, at least for this specific case, the pre-operational Meteosat 12 has for sure more coverage compared, it's the same timestamp exactly, to Meteosat 10. And yeah, so there's more quality, there's more points retrieved, and some of the points, the quality is higher compared to the Meteosat 10. I'm not really exactly sure what that means, but at least to me, that means it's good for our gap filling. But of course, results remain to be seen before we proceed. That's planned for next year. Some of the things we do with the multi-year product, all these that I mentioned up to now were related to our near real-time products. Some of the things we do with our multi-year products is to make ocean monitoring indicators, which we release to the Copernicus Marine Service, and they are available online. So this is the monthly mean and a 1-year moving anomaly relative to the 1991 to 2020 climatology, and this is a standard climatology adopted and also suggested by the WMO. And what we do is also we calculate the average trend for the Baltic Basin, which you see down there. This is up to 2024. The 2025 update is coming soon. And in the same context, we also release a cumulative trend map every year for the trend, the rate of change per year divided by the number of years, in this case also up to the year 2024. Some future evolutions that will come up is the ingestion of SLST-RSSTs from Sentinel-3C, if we make it on time for that, for this Copernicus Marine Service contract. The ingestion of, as I mentioned before, the MTG FCI when it becomes operational. We are looking into the high resolution missions and future perspective to potentially ingest Tristan SSTs. They are going to be very relevant for the Baltic, being an enclosed basin. And as I said earlier, we have tested 4DVAR-net machine learning code and has really good results in our area. There's a publication from Maxime, who is also giving a talk on Thursday, I believe. And we are actually looking now at obsoleting the OI code and having the gap filling being done by the machine learning algorithm. It will not be operational this year, but maybe we will try to do it for next year at some point. And for our multi-year products, we are looking at reprocessing with SST CCI version 4, if that's available on time next year, early next year. And we will also include the AMSAR CCI. So we will include passive microwave observations in the multi-year product. And we are switching the standard annual temporal extension to -6 months instead of -1 year. And we are continuing our standard OMI calculation. And with that, I would like to thank you for your attention and your patience. Yeah, questions.
Thank you, Jana. Exactly on time and nice presentation of the Baltic. So now we open for questions for the two last presentations. Yeah, Sheila.
Testing. Okay, great. Thank you. I just wanted to, the first talk, Kohei, regarding the GHRSST products. Yeah. So they're both GHRSST products. The OISST is a GHRSST product as well as a MUIR product. They're both part of the group. The SSTs, they're both part of the group for high resolution sea surface temperature. The OISST is a GHRSST product as well. And I just wanted to make a note that NOAA has had that product for a long time, and we've been looking at trying to improve it or replace it in general, but it's a very broadly used climate data record that's hard to replace. And so we're looking into improving the product or replacing the product in general, but it is also a GHRSST product, just a note.
So yeah, makes sense. The OSST will be improved. Okay. Yeah, if so, that I'm happy to use that updated data set. Thank you.
Yeah, just one quick note. If it's the MUIR SST product that's being used, you have to be careful using it in the high latitudes, because remember, it's only nighttime data. MUIR does not have any daytime data. So that means in the high latitudes, you could go months without, without any data. So anyway, just a cautionary note, about using MUIR at the high latitudes. Thank you.
Yeah, I think that the nighttime SSTs, for me, it's okay because the diurnal warming can be ignored. So, but still is a problem. I don't know. Maybe, yeah, later we're gonna discuss.
Yes, Chris?
For Joanna, you mentioned that your gap filling may move to machine learning based gap filling. Don't you think there's a bit of a danger in that, in applying that to an area where the climate is changing quite fast because it's tuned to the past only, it's not based on physics?
Yeah, I mean, from what we've seen, the truth is that I'm not that machine learning literate yet. So with a grain of salt, I think if the training we've done for this case was based on a few years of level 3 data. Maybe, and I think it wasn't broken down in seasons, it was random training using random data. I don't know if things improve when, first of all, you expand the training into more years, going back into, for example, a climate data record type of length for training, and then you try to also feed in seasonal variability as well. But for sure, I don't know how static could that be, or if you need to retrain every few years to adjust. But I'm not sure also how static our correlation length scale should be, because we don't update those, or our uncertainty estimates. We don't update those either very often. I hope that touches a bit on the point. Yeah, thanks.
Thank you, Chris. Good point. Any other questions for the two last speakers? What, over there?
I have a question for Iona. You compare with the Argo and the SPUI anything sheep data. So what depths of the observation data you use? I think that did quite varied very much among the data set.
Yeah, thanks for your question. So the products are considered to be foundation temperature. So we compare when it comes to drifters, it's the 20 centimeter standard drifter depth. When it comes to Argo, which we have very few Argo, I think, if I remember from the matchups, it's the shallowest Argo depth, and we try to use the surface Argo, so it's maybe a meter or something.
I see.
Moorings are also not very standard in the area, especially in the Baltic, so it's the top available, the closest to the surface available depth. And for ships, which is normally the intake, the measurement is in the engine intake, we know for sure that our biases are larger, and of course they are not directly comparable, but in these cases we just use whatever kind of in situ measurements we can. The reference is drifters.
Right.
And if we had a lot of drifters, we would only stick to drifters, but that's not the case in the Baltic.
So you mentioned you use try to make a foundation SST, right?
Well, yeah,
right?
it's
Yeah.
considered because it's nighttime only SSTs, and
I
it's
see.
considered the foundation. Yes.
I see. Thank you very much.
Okay, I think that closes the question for the presenters of session 3. Then let's move on to the GRIST priority discussion on this session. So sea and sea ice surface temperature in coastal and polar regions. So that includes also a few task teams, and yeah, maybe it's a good opportunity to come up with new priorities for these task teams, or new ideas for what the task teams could look at. I'm thinking about the high latitude task team, the ultra high resolution task team, and the possible heat wave task team. So yeah, any ideas, any inputs for GRIST priorities on today's issues? Yes, please.
Under the CEOS coast VC, basically these days gap analysis teams have been constituted. So it will be a nice opportunity that for the coastal SST, some of the people who are producing the coastal SST can participate in the gap analysis and provide their inputs to the coast VC team. So I'm one of the co-leads of the coast VC. So if any one of you is interested to participate in that, so that will be quite a good input for the team. Thank you. And also there is a high latitude gap analysis team. So there are two teams. One is the coastal product team and the high latitude gap analysis team.
Thank you. So yeah, at least from my own side, I'll be happy to talk to you afterwards about the polar part. Thank you.
Can I just ask, is anyone in the science team involved in either of those presently? Anyone in the room? Right, okay. So Ed was saying that he was, and so was Jorge at some time, yeah. Okay, yes, thank you for that intervention, Neeraj. I think that's very helpful. We should make sure that's covered.
Just one, from the experiences of working with SST in coastal areas, one thing I think really needs to be looked at seriously, and maybe this is part of the gap analysis, is the issue of cloud cover and how it impacts, the derivation of gradients and things like that. For example, I can use just an example quickly off the California coast, in comparisons between Muir and Ostia. There are times when Ostia does better than Muir. Why? Because we have what we call the June gloom in California, where we might not even have, a cloud-free pixel for a week. So even though one is gridded at a higher resolution, I mean, so I think the cloud, the issues of clouds and data gaps because of them in applications to coastal regions also needs to be looked at seriously. Thank you.
Go ahead.
I was just going to make a comment on coastal SSTs and AI. Are there any approaches in place to help improve our coastal SSTs, perhaps with another parameter, because of our resolution and our sensors and all the various limitations that we have? What kind of current technologies, are there any current technologies that can be used to help provide improved coastal SSTs?
Does anyone want to answer that? I'm not sure. No?
Okay, it wasn't. So, for example, we have been working on a super resolution algorithm, which is machine learning based to improve the spatial resolution of SST. And this works also for coastal regions. So there are tools. Ours was just the start, but you can, enjoy it.
And I think it's an important one, because if we're going to very high resolution and you want to do anything like, well, not marine heat wave, but a degree heating week or anything that has that sort of nature where you need a climatology behind it, we don't want to wait 30 years of high resolution SST data before we can start making such things. So how are we going to learn how to imitate the climatological record. Well, we can only do it from the coarse resolution plus what we're seeing just now, and somehow propagating it back, and possibly machine learning is an approach that could help us with that problem. So I think that's worth noting, and when we see the data, we'll see whether it will work.
In shallow water, especially during periods where there's little to no wind, the tidal currents will dominate the SST because of bottom-up mixing. That's when you get your sea surface temperature patterns. When you have wind, it'll just mix it all up and it'll be homogeneous. That is repeatable over and over and over again simply because the bathymetry doesn't change. So I would think that an AI would be able to cope with this no problems at all, actually. I think the big problem that we're going to have is as climate change progresses, low frequency currents are going to change, and that will change things. You know, in other words, coping with future advection patterns due to advection will be the hardest part. But almost everything else in the coastal sea surface temperature patterns is somewhat repeatable. So it's not quite as an intractable problem as we might think.
So now, actually, we also have this SWOT observations, very high resolution coastal sea level, means not exactly coast, but quite near to the coast. So that data also can be used. Even the dynamical coastal models, if you assimilate this kind of information, high resolution sea level information, what we have seen is that there is a huge impact on the coastal sea surface temperature simulation patterns. So even a data assimilation procedure in the coastal models, they can be used and by employing this assimilation techniques of SWOT, for SWOT. So that can also be explored for physical based generation of the SST datasets.
Okay, anyone else for any GHRSST priorities that we haven't thought about? Or anything you would like to? Yes, please.
Yeah, thank you. As a user of a coastal SST, I think first one I want to ensure that because I usually done some studies on the retrieval of SST, so we know in the open ocean, the retrieval parameterizations might different from the coastal, especially in the, for example, very type 3 or even type 4, where we have very sediment or even riverine inflows that play. So maybe I hope your working group may have some like a super parameterization, especially for coastal region, to recalibration to find some more better coefficient during the retrieval algorithm. Maybe that's what I want to say. Yeah, thank you.
So yeah, back to you, Chris, on what you said about coastal and machine learning. Are we talking about waiting for the ultra high to calibrate the more normal resolution towards closer to the coast, or is that the solution, you think? Yeah, so we need ultra high to calibrate the normal resolution, and then we can go back in time. Yeah. So challenge given. to be reported in breast in 1 year. Yes, I think, yeah, people are now, yeah, we spent a long time in this room, so I think this discussion is coming to an end now. So thanks for all contributions to session 3 and other sessions. Are there any practical information to
Yeah,
give?
I think Misako wanted to share something with you for tomorrow. The details, yeah? Yeah, for the logistics, yeah. Maybe you do that.
So I would like to share with you some logistics announcement. So our poster presenter does, we had announced that the switch for poster display would be tomorrow morning, but please take your posters down when you leave today. I mean, poster presenter in group 1, because poster pitch session for group 2 will be held at beginning of tomorrow morning session. And for group 2 presenters, please display your posters on tomorrow morning when you come here. And also, there is some announcement to the participant for excursion and group dinner tomorrow. So we will meet at venue around 12:50 p.m. after taking group photo. And we will depart Hokkaido University on 1 p.m. And then we stay in Ottawa City from 2 p.m. to 4:20 p.m. And you can enjoy Ottawa City and sightseeing. And after that, we will depart from Ottawa City around 4:30 p.m. and then arrived at the venue of group dinner party called as Sapporo Beer Garden. I guess around 5:30 p.m. And group group dinner will be start from 6 p.m. So there is some notification. So unfortunately, participation is not available for those who have not registered in advance. And please make your own way to Sapporo Beer Garden if you will be joined from the group dinner onward. So it is only a domestic participant. 日本語で話しますけれども、グループディナーから参加される方、日本人と任さんなので、ご自身で札幌ビアガーデンまで来てください。Yeah, Japanese announcement is end. Yeah. So for participant of excursion, light snacks and tea will be provided during the bus ride. The bus ride will be approximately 1 hour. And you can keep your baggage inside the bus during the stay in Otaru City. Baggage or laptops. And in case of emergency, please call the contact number Kachi-san and me listed on the card that will be distributed tomorrow, the small card. And also, there is some announcement for participants of group dinner. So as the grill is shared, so vegetarians are asked to sit at the same table. So there will be, sign indicating vegetarian on the table at the restaurant. Sorry. So, and please wear a shirt that can be washed. Yeah. So since the group dinner will be a Hokkaido style BBQ and the strong smell will stick your clothes. Jackets and bags can be placed in plastic bags to prevent that smells, but you probably won't be able to wear the same shirt again the next day. So please be careful. So, and the final announcement. So please return your hotels from the venue on your own. So it will take 11 minutes by bus or train from venue to the Sapporo station. So if you ask us, the local organizing staff, we can tell you how to get to your hotel, using that public transportation. So the announcement is end. Yeah. Thank you for your attention.
Ishin, then you can walk back to Sapporo station in 20 minutes or 25 minutes. And also taxis are available.